Hello. Yeah. Okay. Good afternoon, everyone. And is my voice echoing?
Yes, your voice is echoing.
Just give me a minute. Yeah, I think like now it will be audible properly. Is it okay now?
Yes, ma'am.
Yeah. Right now. Right. Okay. So, good afternoon, everyone, and welcome. So, on behalf of Digital Technologies, I'm really glad to see all of you here today for our 5 days FTP on quantum computing, powered by Digital in collaboration with qBraid. So, before we dive in, yeah, is there anything, ma'am?
See that interference or distraction is from digital team itself. It's from that end only. So maybe that mic is okay. Thank you.
Govardhani, could you please mute the Digital support account and just speak from your own account? I think that
Yeah,
will.
Yes.
actually, I don't have this digital support account now. I'm having only from my end. Is it still echoing?
Right
Not
now, no.
now. Yeah.
Yeah, now it will be okay. Yeah, it has been done. Okay.
Okay.
Yeah.
Thank you.
Okay. So, sorry for the interrupt. Yeah. Once again, warm welcome to everyone for this FTP on quantum computing powered by digital technologies in collaboration with qBraid. So, before we dive in, let me take a few minutes to set the context for this program by introducing our collaborators and introduce today's speaker. So, a quick word about us. Digital Technologies is a technology solution provider, and we work closely with academia, industries, and research institutions through advanced engineering solutions. So, we work across fairly wide spectrum like embedded systems, embedded AI, AIoT, edge intelligence, FPGA platforms, and test and measurements technologies. So we also enable wireless RF and 5G or 6G research using dedicated tools and lab environments. And beyond just products, we design and deploy complete lab setups like hardware, software experiments, and training. And we have done this across multiple labs, and which you can also see showcased on our websites in short. So our philosophy is simple, like we are building industry-ready engineering ecosystem. So, just to give you a flavor of what we do, our key solution areas include automated test and measurement, AI, and machine learning. So, FPGA and semiconductor design, 5G or 6G wireless research, as well as quantum and optical solutions. So, quantum is very much a core part of what we do and not something new we have just picked up. So, and we don't do this alone. We collaborate with some of the excellent technology partners like ST, Digiland, qBraid, Mantis Wave Networks, and TMY Tech, Crobot Technologies, QU Tools, and Emona Teams. So, these partnerships help us bring you real industry grade tools and platforms rather than just a theory. And now, specifically for this program, our collaboration with qBraid and Digitoad have come together to bring structured quantum computing education to the academia as well as research institutions. So, qBraid gives us a web based quantum computing platform that supports learning as well as development and experimentation. And through it, you will get to work with multiple quantum frameworks, simulators, and even real quantum hardwares, all through one unified environment. So, together, we support teaching, academic labs, and research workflows with guided content tools and platform access. So, that's exactly the experience we have designed for you over these 5 days. Now, let me introduce the person who will be guiding you through today's first half, Mr. Harshit Gupta. So, Harshit is a quantum software engineer developer at qBraid. So, with over more than 2 years of experience in the field, and his area of expertise lies in quantum transpilation, compilation, and distributed systems. And he's actively worked on some well known projects, including PyQuasm, qBraid SDK, and qBraid QIR. So we are really fortunate to have someone with hands-on real world quantum software experience walking us through the concepts and the qBraid platform. So just to quickly touch on the structure of this program, Harshit will be taking today's first half session, and I'll be joining in and taking over the sessions from the second half onward. So for the remainder of the program. So, without further delay, let me hand it over to Harshit to begin the session. Harshit, over to you.
Thanks so much, Govardhani, for that introduction. Just want to make sure that my voice is clear and my video is coming up correctly, right? Govardhani?
Yeah, Harshit, it is clear.
Okay, perfect. Yeah. Welcome all. Welcome to the faculty development program that qBraid and Digitoad have arranged for all of you. Over the course of 5 days, you'll be learning about, what quantum is, how you can interface with different quantum systems, and how you can learn about the mathematics inside this field. I'm very excited to start off with today's lecture. And without further ado, let me just share my screen and then we can get started. Is my visible over the
Yeah, it is visible, Harshit.
Okay, I think I seem to be getting some echo from again the digital support channel side. If you could mute that account, I'll be very great.
Yeah, I'll check it out.
Sure. Yeah. Thanks. Okay. So, hi everyone. My name is Harshit. As Govardhani mentioned, I work as a quantum software engineer here at qBraid, and my major experience has been in quantum transpilation, compilation, distributed systems, and
Hello, everyone. Welcome back to the session. I Before starting the session, I just want a confirmation from you guys, like who and all have the account already like created on the qBraid. Like if not, we can create the account for everyone at once. I can show you the steps to create. If it is not created, just drop in the comment section like not created.
Hello, ma'am.
Yes, ma'am.
Um, Actually, I am doing one IBM course, summer season
Okay.
course. Okay, it is mainly a qBraid only. I already created account about it. Account on
Okay,
it.
ma'am. No issues.
So
No issues.
we can use the same, right?
Yes, yes, you can use the same thing.
But it was mentioned 100 hours, but 31 hours I used for that
Yeah,
course.
so free trial access will be having 100 hours by default, ma'am. It will be
Okay.
like depending whenever you are starting the server, your timings will count on.
Okay,
Countdown will start.
for
So
our purpose, this remaining time is enough, I guess.
yes, ma'am, it is enough, more than enough.
Okay, okay, thank you.
Okay, ma'am. Okay. So I guess most of them have not created the account. Okay. So let me guide you through the steps. Okay. So I think Harshit have guided you guys to go to the account.qbread.com, right? So you guys can go to here. Okay. So open your browser and you can type qbread.com. Okay. If you already have the account, you can just log in and you can be in this page. Okay. So I'll guide you with the next steps later. And who have not created the account, you can just click on the sign up option. Fine, it is getting logged in because I have already created the account. So when you click on the sign up option, you will get redirected to the credentials part where you need to give the like mail IDs, names, and password. Okay. So once you have given that, you will get a verification link in your mail IDs. Okay. Once you have done that, your account will get verified. Once you have done that part, kindly let me know in the comment section like it has been done. Okay. Or if you are facing any issues, just let me know.
Overtini, you are muted.
Oh, sorry, ma'am. Yeah,
Thank,
thank you.
thank you.
Yeah. So once you have created the account, you can just log in. Or if you have not created, click on the sign up and give the all the credentials. Once it is done, your mail ID will get the verification link. Okay, you can just verify the account and you can log in once again. So let me know once everyone is on this dashboard page. Okay, you can drop the comment in the comment box saying that account creation is done so that we can move to our today's learning session on the theory as well as practical aspects. Actually, don't launch any instance yet. You can just click on stop launching the instance. If you have created, you can just click on this stop. Okay. And be on this dashboard page. Don't launch any instance yet. We need to actually redeem the credits part. Okay. So which we will be requiring in future programs when you are running it inside the hardware. So for that you will be requiring credit points. So wait until I give you the next instruction about launching the instance. Okay. Does anyone still need time to create the account or shall we proceed? Yeah. Okay, then we'll proceed with our credits part. Okay, so everyone here, you can just scroll down. Fine. This account session, if it is not elaborated, you can just click on this expand option, and here you will get the wallet option. Okay, so go to this wallet option, and yeah, so in the promo code you can type $5. Okay, and you can just click on purchase. Oh, okay, sorry, just give a minute. Am I sharing my screen? Yeah. So the qBraid code for this. Yeah. So in this promo code, you can type qBraid 5. Okay. In caps, qBraid 5. Sorry, like if you guys have any queries, drop it on the chat so that we will not get any echo or any sort of disturbance for others. Okay. I'll check it out. Once the steps are done, I'll check it out. If you guys are stuck somewhere, I'll help you out with that. Okay, so in the promo code, you can drop the text that is qBraid 5. Okay, and you can click on purchase.
Kavatini, what is the promo code we have to write?
Sorry, ma'am?
What is the code?
That is qBraid 5. I'll just drop it in the text box. Okay. Okay, so like let me do it with the other account. Just give me a minute. Okay, from my end, it is not doing because I have already used it. Okay, you guys can do the steps and let me know what you are seeing here. Okay, so once you have clicked on purchase, I think like you will be redirected to the add to cart option, right? Am I correct?
Yes, yes, yes.
Yeah. What options you can see there?
Like I have the currency which is mentioned as 498.71. One is dollars, dollar US dollars 5. And then pay
Okay.
securely with some link, uh, email, and
Okay. Can anyone share the screen? Actually, I'll just stop sharing the screen. If possible, Manjula ma'am, can you share the screen?
sorry, actually, I'm recording the session, so I'm trying to do this on my mobile phone.
Okay, okay. So, if anyone voluntary are there, like, yeah, thank you so much. Okay, so you can click on this complete order. Yeah. So, I think like 500 credits would have been added to your account now. Let it get loaded. Yeah. So you can see here 500 credits have been added to your accounts. Okay. So this is how you can redeem the credits. Yes, ma'am.
Can you just once again elaborate this step because I just missed that point. I have to click on $5.
Yes, ma'am. And then here the promo code should be qBraid 5. Ma'am, I think like your credits have got added.
No, mine I don't know
Who is
where.
the one screen sharing, ma'am?
No, I'm not the one who's sharing the screen.
Okay, sorry, ma'am. Then. Okay, so I think they are also typing to show you the steps. Thank you.
Okay.
So here in the code, you need to type that qBraid 5, and then you can click on the purchase option.
Okay.
So in that part, you will get redirect to the like add to cart options. Okay. So in that amount would have been deducted to 0. So you need to click on the complete order so that 500 credits will get added to your account.
Okay, fine. Yeah. Thank you.
Okay.
We should choose $5, right? While choosing.
Yes, ma'am.
Sorry. Govardhan, do we get recording of these sessions?
Yes, ma'am. Sure. We will share it to you by the end of the day itself.
Oh, then okay, fine. Thank you.
Yeah.
Hello, ma'am.
Yes, ma'am.
Ma'am, after selecting the $5, what should we do, ma'am? I missed my step. Sorry.
Okay, ma'am. No issues. So in the coupon code, I think promo code option will be there, right? So I'll just share this.
Yes.
Yeah. So in that you can type qBraid 5. Everything should be in caps.
Okay.
Okay. I have dropped the like coupon ID also like this. You need to type.
Okay, ma'am.
And click on the purchase option.
Okay.
And then you will be redirected to the cart option. At that time, you can click on complete order.
Okay. Thank you, ma'am.
Okay, no issues. So I guess everyone's like issues have got solved. If not, you guys can drop the message. Not done. Everyone's coupon have got added. Okay. So then today we'll move on to our reading session. Okay. So like welcome back for the second half of the day one. So in the first half, like Harshit walked you through the broader landscape of quantum computing and got you comfortable navigating the qBraid workspace. And in the second half, we are going to slow down and really build up the core concepts from the ground up. Okay, like from qubits, superpositions, a first look at entanglement and how quantum circuits are actually structured. And of course, we will close with our second hands-on lab of the day also. First was about hands-on creation, which we have done now. And next, we will be working on single qubit execution lab using the qBraid platform. Okay, so here is our roadmap for this hour. So we will cover qubits, superpositions, and we will also get you a preview of entanglement, and you will also understand quantum circuits, and then move into the lab 2, where you will run your first circuit involving the superposition. Okay, so let's begin building these concepts one at a time, and starting from the most fundamental building block, that is the qubit itself. So what is a qubit? Okay, and let's really unpack this. So in classical computing, everything you have ever used in your laptops, your phones, every websites ultimately reduces to bits, and the bit is rigid, right? It's either 0 or 1, like a switch. It's either off or on, right? So there is no middle ground, no ambiguity at all in this bits in the classical one. So a qubit throws that rigidity out of the window. Like a qubit doesn't have to commit to being purely 0 or purely 1. So it can exist in a blend of both simultaneously. Okay, so think of spinning a coin in the air. While it's spinning, it isn't really heads or tails, right? So it's some combination of both possibilities, and it only settles into one state the moment it lands and you look at it, right? So that is what we call it as measurement. Now, why do we write it as 0 plus 1? Because those A and B values are called as amplitudes, okay? And they are not just descriptive, they carry real information. Specifically, if you square their magnitudes, right? Like A square as well as magnitude of A square and magnitude of B square, you get the actual probability of measuring 0 or measuring 1. And since probabilities must add up to 100%, that's exactly why a square, like a square plus b square, is always equal to 1. And this isn't just theoretical math, okay? So qubits are physically built today using very different technologies. Some companies use photons of lights, and some use trapped ions suspended in the electromagnetic fields, and others use the superconducting circuits cooled to nearly absolute zero. Okay, and different hardware but the same underlying quantum mechanical description. So I'll pause here, and I would like you to think about this and share your thoughts in the chat in your own words. Okay, so how would you explain the difference between a classical bit and a qubit to a student who has never heard of quantum computing? Any answers, like how you will be explaining about the difference between the qubits and the classical bits to the students who are new to the quantum computing era? They don't even know like quantum computing exists at all, right? But you want to bring the awareness to them. So how will you be starting it? Okay.
Ma'am, can I?
Yes, ma'am, you can.
Okay, so as per my point of view, first of all, explain the thing in a classical beat work, like it is use 0 and 1, and it is at a time in a single state get the state, and quantum bit is always in a multiple state at the same time. So it is work like both. Like they work in every state at the same time. So it is a different thing between a classical bit as well as in a quantum bit. It is in a classical bit, or classical computer use only bit 0 or 1. That time we can store 0 or 1 in a single state. But in a quantum bit, always stay in a multiple state at the same time. So that is the difference between a quantum bit and uh, normal bit.
Yes, ma'am. So, Dharmishta ma'am, yeah, that was a great answer from your side. Yeah, that is what exactly we feel the difference between classical as well as qubits, right? So, for example, imagine like you have entered the mall with three friends, okay, and one of your friends have gone missing, and you have only two people now, right? So what you guys can do, like, one guy will go, and if it is a classical bit, what will happen is you guys will be starting from the first floor in the order, right? And then you will be moving to the second floor, and then to the third floor, and to the fourth floor. But if it is a qubit, right, like what happens it is two people can be appearing like in between of the floors. Like it is not like you should start from the first floor itself. So at that time what happens, like you can be present in the first floor, at the same person can be present in the third floor also, right? So at that time what happens, you'll find the person at the faster rate. So that is what the major importance qubit is holding nowadays. Okay, so it was a great answer, ma'am. Thank you so much. And Bona ma'am, thanks to you also. You have also dropped the correct answer in the comment box. Like if you guys can not if you can't unmute, you can just drop the answers in the comment box. I'll just read it out for you. Okay. We'll keep this session interactive and not like only I'll be speaking and you guys will be just listening to me. Okay, we'll keep it interactive session. Okay, so now let's go deeper into the superposition itself. Okay, so because this is the really the heart of what makes quantum computing fundamentally different from the classical computing, right? So I want to correct a common misconception here right away. So superposition does not mean we don't know if it is 0 or 1 yet. Okay, that's not it at all. So it genuinely means that the qubit is holding both possibilities at once. Okay, so as a real physical state, until something forces it to commit, like here's an analogy I like. Imagine standing in at the fork in a road. Okay, so and instead of choosing one path, you could somehow explore both paths simultaneously. Okay, so gathering information from both routes at once. So that's the spirit of what a qubit in superposition is doing. Now, how do we actually create this, right? So we use something called as HADMAT gate, and think of it as a tool that takes a qubit sitting quietly in the zero state and pushes it into the perfectly even blend of 0 and 1. So, but here's the fragile part. So the instant you measure it, right, the superposition qubit, the moment you measure it, that blend collapses. So the qubit is forced to pick one definite outcome. And that's precisely why in quantum computing, we never rely on a single run. So we run the same experiment hundreds or thousands of times because only repetitions reveals the true underlying probability pattern, right? And yeah, we'll have another question on this slide. So why do you think measurement destroys superposition instead of just revealing what was already there? So what does that tell us about the nature of observation of quantum mechanics? And go ahead and drop your answers in the chat. Yeah. Okay. Okay. So let me answer it then. So measurement changes the quantum state because the act of checking forces it to pick. Sorry, ma'am? Okay. So I just request all the participants to mute yourself so that it will not cause disturbance for others. Okay. Yeah. So let me answer this question. Sorry.
My laptop is not supported. Wi-Fi.
Jayanti ma'am, can you mute yourself? Yeah. Thank you. So let me answer this question. So why do we think this measurement destroys? Because measurements changes a quantum system because the act of checking forces it to pick one definite state, unlike the view that is simply uncovers hidden pre-existing reality. Okay, so why measurement changes the system? Like dual particle nature, wave function, it will get collapsed, right? So the math of quantum mechanics shows a system as a wave of many possibilities until it is touched by an external device. And we also know quantum entanglement with the environment. So the measuring tool interacts with the tiny particles and it will be scrambling its hidden options and locking it into the single results. And you can also you would have also learned about the Bell's theorem, right? So it will be proving you that particles do not carry secret or preset answers before someone looks at them. So what this tells us about the observation is looking at a system is not like reading a thermometer. Okay, so it is like a physical action that forces a choice, and like the subject object will be like blurred. So the boundary between the observer's tool and the quantum object becomes unified during the exact moment of the test. Okay, so the quantum states behave more like rules for what we can know rather than solid blocks of hidden matters. Yeah. So thank you for the participants who have tried their best to answer this question. Okay. Yeah. Now, just a preview of something even stranger, that is entanglement, right? So imagine two qubits whose fates become linked, okay, such that knowing the state of one instantly tells you sorry, so tells you something about the other. So no matter how far apart they physically are, it's almost like having two coins that no matter where you carry them always land in matching outcomes. Okay, so classical physics has no clean explanation for this kind of correlation, but quantum mechanics allows it very naturally. So I want to be upfront. So today is just a glimpse. Okay, so we are not building the entangled qubits in this session. That's the entire focus of the day 3. So where we will create and verify the entanglement hands-on using the Bell states. Okay, so for now, just the takeaway is that entanglement is a correlation that goes beyond anything, okay, classical bits can replicate. Fine. So for here, you can drop your thoughts in the chat. Okay, can you think of any real world analogy, even an imperfect one, no issues, that captures the spooky feeling of entanglement? So you can share whatever comes to your mind, which will tell you about the entanglement state, any of the real world applications. You can share your thoughts in the group, in the chat. Like any of the real world applications which will bring you a thought about entanglement. You know what is entanglement, right? It will create the correlation between the two qubits. Like if you are able to read the state of one qubit, it is more than enough to tell the state of the another qubit, right? So is there any real world application so where which you can tell as an analogy for entanglement?
Ma'am, Jayanti ma'am. Ma'am, this is Jayanti.
Yes, ma'am.
The correlation between disease and then symptoms.
Yes, exactly. Yes, ma'am. You can tell, yeah, predicting about the disease, you can tell the symptoms, or seeing the symptoms, you can tell the disease. That was a very good example.
Yeah, thank you.
Thank you, ma'am. Any other things? So this examples, whichever comes from your side, right? This will explain how well you are like having the good knowledge about that specific topics. So that's why just give it a thought, like whether how you are thinking about entanglement will be. Yeah, synchronized dance partners, I can say like coordination, right? Coordinated dance partners, you can say that. But if the steps are different from each other, it will be a little bit difficult, because it will be not every time, it will be not same. But entanglement, it is every time, it will be, there will be a correlation between them, right? But yeah, but we can say this example under that certain conditions.
Ma'am, one more example, music and state of mind.
Music and state of mind. Yeah. Yes. Okay. Yeah, that's deep, ma'am. Yeah, that's good. And have you observed about like a very common example in rolling the dice? Like whenever you are rolling two dice, right? So when the first one is stopping, simultaneously the second dice almost it will get stopped together with the first one, right? So the movement of the dice you can say, but we can't say the number of the both dice will be same, but we can say that movement will be same, right? Yeah. Okay, then I'll just resume with the concepts next. Fine, that was a good interaction. Okay, so let's now talk about how all of this come together in practice. Okay, so through quantum circuits, think of the quantum circuit like a recipe or a flowchart that tells us precisely what operations to be performed and in what order. Okay, so each qubit is represented as an horizontal line and almost like a timeline, and as we move left to right, we apply gates to it. Okay, so we have already met a hard-math gate, right? So which creates superposition. There is also the X gate, which simply flips a qubit from 0 to 1 or vice versa. So much like a classical NOT gate. And there is a Z gate, which changes the phase of the qubit. And a more subtle quantum property, we won't dive too deep into.
ఏదో రాజీనామా కూర్చున్నాడు కూర్చోండి కూర్చోండి సార్ ఆయన కూర్చోండి
Satish, sir, can you mute this?
తగ్గిపోతుంది మా ఏంది తగ్గిపోతుంది
Satish, sir.
ఓకే ఇది ఒకటేనా ఇది అయిపోయింది కూర్చోండి చేసావా
all the participants put in.
ఒరిజినల్స్ ఇచ్చావా?
ఇవే ఒరిజినల్స్ ఇవి కాదు కదా
ఇదా 5 సార్లు సబ్మిట్ చేయనా?
అది ఒరిజినల్స్
I'm not able to do it actually. Satish sir?
Shiva,
Yeah, I think he's on mute now. Fine. Yeah. So we were speaking about XGate, right? So there is also the XGate, which simply flips the qubit from 0 to 1 or vice versa, and much likely like classical NOT gate. Okay. And there is a Z gate also, which changes the phases of the qubit. A more subtle like quantum property. We won't dive too deep into it today. And at the very end of every circuit, we perform measurement. Okay, so this is the step that takes the qubit out of its quantum blended states and converts it into something familiar, an ordinary classical 0 or 1 that we can record and analyze. Okay, so the great part is we don't need to imagine this abstractly. So the qBraid quantum lab lets us actually build these circuits gate by gate and run and visualize them directly in the browser. So which brings us into the today's lab. Okay, so for this lab, our objective is straightforward. We are going to build a single qubit circuit, put that qubit into superposition using the Hadamard gate, and then measure it across many shots to actually observe the probability pattern for ourselves. Okay, instead of just hearing about it. Okay, and here's what we will do. Open a fresh notebook in the qBraid quantum lab, and we'll create one qubit circuit, apply the Hadamard gate, add the measurement step, and run it on the simulators. Okay, so you guys can navigate to the qBraid part here. Okay, I'll just... Okay, I think I can't upload the file here. I'll just upload it into the drive and I'll share the link. Yeah, sure, ma'am. We will provide it at the end of the session. Yeah. So in the chat, I have dropped the link. Okay, drive link. You can go to that folder. And you can download the file which is present inside that IPYNB file. So everyone will be able to see this file, right? You can just download it as it is. Everyone have downloaded the file? Can just give me a thumbs up. Okay, so now everyone will be on the dashboard page, right? So you can just go to the dashboard, and here can you see the small instance launch option? So can you click on that so that your instance will get launched? Okay, so once you have done, you can click on the Open Lab. Fine. Okay, so once everyone is on this page, you can just click on Add Folder. Okay, you can just name it as. Yes, ma'am.
Sorry to interrupt. So after we go to our dashboard, what is the next step?
You need to launch that small instance, ma'am.
Okay, small instance. Okay, then that's it's prompted.
Yeah, it will get loaded and it will give you the option saying Open Lab. Once it is loaded, you can wait until then.
Okay. Yeah, hi. Thank you.
Yes, ma'am. So you can create the folder here. Fine, I'll just rename it to 5 days FTP, right? We'll keep it 5 FTP and I'll open it. So here I'll create another folder. If I double click or right click, we'll get this option and I'll create day 1. Okay. So inside this, you can go to the upload option here, right? So you can click on this upload file and you can upload the downloaded file here. Okay. Or you can also just drag and drop, like you can just do like this. So it will get copied here. Okay. So once this is done, fine. So we need to create the environment for our lab setup, right? So in that which we can install our required libraries. For that, you can just go to the environment here, this option. It will be empty for you guys, or if someone have attended a quantum summer school program, you will be having QGS's environment. Okay, you can ignore that and you can click on the add environment. Okay, and you need to click on create environment. Here you can give any name for your environment. I'll just give day 1.
Wait a minute, madam. We didn't do that.
Yes, no. Sorry, sir. Where are you, sir? In which step you are stuck, sir?
We are able to create the name of the file first.
Okay.
Hello, madam.
Yes, sir.
We are unable to create
You
the
want
name
me
of
to
the
help?
file here.
Okay.
Huh?
So you can just click on this new folder. Okay. So your folder will get created. You can give any name for that. I have given 5 FDP. And inside that, you can create the subfolder also. Like if you go inside this and if you create another folder inside this, it will create the subfolder. And I have given it as named day 1. Okay. So inside that day 1 folder, I have uploaded the document which I have downloaded from the drive. So you can click on this upload option and select the file which you have downloaded. Or you can just keep the split screen and you can just drag and drop. Is it done, sir?
Day 1, I put the name, but what is the another thing that we have to do?
Inside that folder, if you navigate, there is an upload option here. You need to click on the upload.
Suppose if we have to put a new file. We have to put new file.
No, sir. No.
Uh,
You need to just click on the upload option and you need to select this file. You don't need to create new file.
it is opening. It is opening our open file dialog box.
Yeah. Did you download the file from this drive?
No, I did not download it.
So I have dropped in the comment box like the link to download this IPYNB file. Can you download it from there?
Where it is now?
Sir, it is in the comment box. I have pinned the comment also. Did you get it?
No.
Sir, it is there in the chat option, sir, chat box.
The link have been reshared, sir. Can you check it now? Okay, so we'll move to the next step about environment creation. Okay, so you guys can click on this environment. Okay, and I'll just go back to the step. Okay, so yeah, so you'll be in this page where your environments will be empty. No need to worry about it. These are environments I created for my projects. Okay, so you can click on the add option and click on the create environment. And here you can give name about your environment, anything at your will. So this one I'll give for mine. Okay. And you can give any tag and click on tab. Okay. So once it is done, you can click on the create option. Your packages will get loaded here. Okay, once everything have been installed, you can go to the more option here. Okay, and if you scroll down, here you can see the add package option, right?
One second.
Yes.
Yes. So after giving the description as well as naming as day one, there's the next option. The create option is not enabled. Is there any other settings I have to do? Tags.
Ma'am, yeah. So in this tag, when you are typing, right? After typing the tag, click on tab. Okay, so it will get added. So in tag option, what to create? You can just create any keywords, ma'am. Archana, ma'am, you can add any keywords there and click on tab option.
Okay, thank you.
Yes, ma'am. So once it is done, create environment option will be enabled.
Yes. Got it. Thank you.
Okay, so you can click on the more option here and scroll down on the side panel and you can click on the add package. Okay, so here you need to add Qiskit. Okay, So in this, you can select the latest version. There is no specific version you need to install. You can click on the latest version and click on add. I'll type the keywords you need to search. One is Qiskit, next Qiskit AER for the simulator access, and next is Matplotlib library. Okay, so again you need to click on add package and then you need to search it here. Okay, so and you can download the latest versions in every packages, and again click on add and download matplot library, add. Okay, so download all the three libraries which I have shared to you guys. For every package adding, you need to click on the add package and then type the name and click on add package again. No, don't download Matplotlib inline. You need to click on the, you need to go to the add package here. Okay. First, you need to click on the add package and then search for Matplotlib library. The keyword which I have shared in the chat box. So you will get that Matplotlib.
How to know that we have successfully added these packages or libraries?
Yes, and that I'll tell you in the next step.
Okay, sure.
Okay, so yeah, once you have downloaded all the packages, you can just come back to this page, and here you can see the Python IPY kernel, right? So here you can, in the drop down, you can select the environment which you have created. Okay, so I have created as day one environment, right? So if you have created, you will get that environment here and click on select.
No, after adding those packages,
Yes, ma'am, you need to do this step. Like you need to select the kernel. You need to click on
the top
this.
right one.
Yeah, top right one. Here you need to select in the drop down. You can go to the Python 3 day one and click on select option.
Correct. Sure. And that whatever IPYNB file we have taken existing kernel, that we have to select, right?
Yes, ma'am. You need to keep this file open, IPYNB file which you have created. You keep it open, so you will get this option. And you can click on the drop down and select the environment which you created today. Okay, so once you have done it, here you can see the restart the kernel option.
Madam, can you repeat once again this one?
Where, ma'am?
Python environment, adding the Python to this. Sorry, environment to this window.
Okay. So here you can see the environment options, right?
That I have done.
Okay. Did you add the packages, ma'am?
Yes. Package, I'm not getting the Qiskit AAR.
Oh,
I guess
Qiskit,
on
yeah,
the
yeah. You need to search, like, you need to click on the add a package here option is there, right?
yeah.
So you need to click on that first,
Uh,
and then you need to type Qiskit
okay.
-AER.
Okay.
So you'll get this.
Okay. Fine.
How to do the environment, madam?
Yes, sir.
How to do this environment thing first?
You in the environment creation step, sir.
Yes, I require it. I
Okay,
put only
sir,
day
can we
one
do
as
one
the
thing like-
folder.
Yes, sir. Can we do one thing like at the end of the session, I'll share the video. You can follow the steps there. I think we are already running out of time. Can we do that? Like, if you have any questions, like if you faced any queries, we can meet up in the tomorrow session also.
Okay.
Yeah. Okay. So, fine. Once you have created the kernels and you have selected the kernel here, you can click on the restart the kernel option. Okay. And click on restart. So whenever you are creating the environments, new environments for the same programs, or if you are adding the packages or installing new packages, every time you need to restart the kernel. Okay. So once that is done, so if you run this, right, you will not get any errors. That's how you will get to know all the packages have been installed. Okay. Fine. So everyone is able to run all the cells here. Is anyone facing issues? Anyone facing issues? Like errors, do you guys getting errors? Like without creating the environment, if you're running it, it will be causing errors. If you guys are stuck with creating the environments, we will share the recording of the session by the end of the session. Okay, so you guys can look into that and work on the step by step. Okay, so yes, ma'am.
I am getting one error here, but maybe because before I reload, if there's one more step you suggested, after adding all the environments, one option you showed me, like Python 3 kernel, that part is what we were waiting. I was waiting to check.
Okay, I guess like in the kernel part, it is throwing you error. So what you need to do is, like you have created the kernel with some specific name, right? Like maybe day one or something else. So that one will be present here. So select that particular environment and click on the select option here. Once that is done, click on the restart the kernel option here.
Sure.
Okay, so once you restart the kernel, you'll like all the errors will be gone and you can rerun the cell. Okay, so now let me walk you through the codes. So first what we are doing, we are importing the quantum circuit class here, which is used to create and manipulate the quantum circuits. Okay, and next we are importing AER, Qiskit simulator package. Since we are not using the real quantum computer at the basic stage. Okay, in the future, like in the next classes, we will be using it. So for now, for the basic state, we are going to use the simulator one. Okay, so we need to install that specific package. Next, we are importing the state vectors, so which is used to inspect the quantum state before the measurement, what it is. Instead of getting only 0 or 1, it tells us the amplitudes of the qubits. Okay, next we have the visualization. So these are like used to display the measurements results in the histogram. And next we are importing the matplotlib libraries. It is for displaying the graphs. Okay, so next we have backend. So it will select the AER simulator. So every circuit will run on this particular simulator. So next we are going to create the state vector. So this particular line of code will create a quantum circuit with 1 qubit. Okay, with initially the qubit state will be in 0. We are initializing the qubit in the known state instead of blindly applying the gates to it. Once you have done that, we are going to apply the HADMAT gate to that 0. At that time, what happens? The HADMAT gate converts 0 into like 0 or 1, like 50% chance of measuring 0 and 50% chance of measuring 1. Okay, so this instruction, it will calculate the quantum state. And in the output state, you can see the amplitude of 0 is 0.7071 and even amplitude of 1 is also 0.7071. Okay, so probability of this is 50% of 0 is available and 50% of 1 is available, which means it is in the superposition state. Okay, so now what we are going to do is we are going to create one quantum bit and one classical bit. Okay, and the classical bit stores the measurement results. Okay, so next what we are going to do, we are going to apply the HADMAT gate to the known qubit. Okay, so state will become now into the superposition, that is 0 as well as 1, right? So when you click when you add the measure option, so quantum bit 0 and stores it in the classical bit 0. Okay, so the results will be, it will be running the, we will run the experiment for 2048 times. Okay, so each run is called as a shot. Okay, so instead of measuring once, the simulator repeats the experiments many times to estimate the probability. And we are going to plot the histogram, like display the result in the histogram part. You can see here, like even though if it is not exactly 50-50, but it is nearly the 50-50 output, right? So if you add these both the outputs, it will be 2048. So nearly equal results confirms that HADMAT gate creates the 50-50 superposition. Okay, next we have the poly X gate. So first we are going to create a fresh circuit. Okay, and initial state we are going to give the 0, and we are going to apply the poly X gate to the to that 0. What is the poly X gate? It is usually a classical C0 gate, that is flipping the bit gate, right? So here it will flip the 0 into the 1, right? So at that time, what happens when you are going to measure and display the result by running the shots for 2048 times, the result should be 1, right? So we are getting the result as 1. So that confirms that poly X gate will be flipping the bits. Okay, so these are the circuits, like these are the gates which will help us to build the larger circuits. Like for example, if we are going to perform one specific operation where you want to flip the bits, or if you want to create the superposition, you will be getting the help of these circuits. Okay. Yeah, so that brings us to the end of today's session, and with that we also wrap up day 1 of our FDP. So before we close, I would like to open the floor for any final questions you may have about qubit, superposition, entanglement of quantum circuits, or anything from lab 2. Please feel free to type your questions in the chat. Okay.
Right now, just now I downloaded that file from the comment box.
Yes, sir.
Then how to do the remaining things? Can you please tell me, madam?
Yes, sir. I will be sharing you the recording of this session, sir, because it is already 5:15. We have been exceeded 15 minutes extra. Okay, so even I have the meeting to go with. So no issues. That's what I said. I'll be sharing you the recording. You can go through the steps. And if you face any issues in that, I will just help you with in tomorrow session.
Okay.
Okay.
Thank you. Thank you.
Yeah. Thank you, sir. Yeah. So I want to sincerely thank all of you for your energy and participations today. And from the discussion to the like lab exercise, it's been a great start to this program. And a big thank you to Ashit as well for leading us through the first half so well. We will see you all tomorrow for day two, where things get even more exciting with two qubit systems and the CNOT gate. So thank you once again and have a wonderful evening ahead.
Okay, thank you. Same to you, madam. But let us complete this particular one tomorrow at least. Otherwise,
Yes, sir.
otherwise it will be difficult for us to do.
Sure, sir. We'll do it off.
Okay.
Yeah, thank you so much, Sujata ma'am. Yeah. Yeah. Hello, everyone. Good afternoon. And welcome to the day two of our FDP on quantum computing using qBraid. So today we are going to spend the next 3 hours moving from single qubit system, which we spent all of yesterday's building a strong foundation in, into two qubit system. Okay, and specifically into understanding how one qubit can influence another qubit through what we call controlled operations. So let me share my screen first. I hope my screen is visible and I am audible properly. Yeah, thank you, ma'am. Thank you for the confirmation. Yeah, so we will be having the Q&A session at the end of this today's day two. Okay, so we'll give you 15 minutes where you can drop your whatever Q&A session you have on today's program or today's concepts on understanding. So we will work on that solving. If not possible on today's session also, you can reach out to me through my LinkedIn account. Okay, I'll be active in that, and you can share your interest or thoughts or any requirement or supports you need from my end. Okay. So yeah, I want to set some expectations for today's session. Like yesterday, everything we discussed revolved around a single qubit in isolation, right? So, how it could exist in a blend of states, like how measurements affects it, and how circuits are structured around it. So today marks a genuine shift in complexity because the moment you introduce a second qubit into the picture, you are no longer just dealing with two separate independent system sitting side by side. You are dealing with a combined system that has to be understood as a whole, and that distinction is going to occupy a significant part of our conceptual discussion today. Okay, so we will be working on the qBraid quantum lab platform throughout, and just as we did yesterday, and everything we discussed theoretically will be reinforced through hands-on lab work, so that the ideas don't stay abstract. Okay, so you will actually see them play out in front of you. So let me walk you through today's structure before we dive in. So you have a mental map of where we have headed, right? So we are going to begin with multi-qubit states and controlled operations. So this is the conceptual foundation for everything else today. And once we understand how multiple qubits are described together and how one qubit can be used to control an operation on another, we will move specifically into the CNOT gate. Okay, so which is the most fundamental and most widely used two qubit gate in the entire field of the quantum computing. And almost every quantum algorithm you will ever encounter, from the simplest teaching example to the most advanced research level algorithms, rely on the CNOT gate in the some form or the another. So after we build up the theoretical understanding, we will move into the lab 7, where we will actually implement the state vector to identify whether we have created the two qubit system or the not. Okay, and in the second half of today's session, we will actually implement the CNOT gate ourselves and observe its behavior directly. Okay, so yeah. So before we move forward, I think it's worth taking a few minutes to properly consolidate what we covered yesterday, because everything today builds directly on top of it. So we began yesterday by discussing the broader landscape of the quantum computing as a field, where it currently stands, what kind of problem it's being applied to, and importantly, how a platform like qBraid fits into that landscape by giving researchers and learners structured access to the quantum computing tools like SDKs, as well as simulators and eventually real quantum hardware. So, all through a unified environment. And this context matters because it helps frame everything we do in this program. And we are not just learning abstract theory, we are learning to use tools that are actively shaping ongoing research and education in this field. So from there, we moved into the actual fundamental of the quantum information. Like we discussed what a qubit is and how it differs from the fundamentally from a classical bit, and where a classical bit is committed to being zero, either zero or one in every conceivable instance. So a qubit is capable of existing in a blended state that incorporates both possibilities simultaneously. So right up until the moment it is measured, like we discussed in the superposition in that in some depth, right? So understanding that it isn't matter of uncertainty or lack of knowledge, it's a genuine physical state of the combined possibility that exists independently of whether anyone is observing it or not, and that is the state only resolves into a definite outcome at the point of measurement. And we also touched briefly on the entanglement. So though we deliberately kept the discussion light, since entanglement deserves a like and will receive a full dedicated session later in this program on the day 3. So yesterday's purpose was simply to plant the seed of this idea, so that we can when we return it in depth, it will be like a groundwork for you which is already present there. So we closed yesterday's sessions by discussing how quantum circuits are structured and the idea that a circuit represents a sequence of operations applied to qubits over time, and that even circuit must eventually conclude with a measurement step, which is what allows us to extract classical readable information out of the quantum process, right? And then importantly, we didn't just discuss this abstractly, we actually built and executed our very first quantum circuit together, that is hands on the qBraid platform. Now, everything from yesterday was confined to a single qubit. Today, we deliberately move beyond that boundary and we start asking what happens when two qubits are present in the same system. And crucially, what happens when we allow one qubit state to influence what happens to the another. And this is a conceptually significant leap, and I want you to actively hold on to the ideas from yesterday's as we build on top of them, because nothing today makes sense in isolation from what we have already covered in the yesterday session. So let's now formally begin today's first block of conceptual material. So our focus for this first session is twofold. That is, first one is understanding what is actually means to describe a state involving multiple qubits together, rather than describing each qubit on its own. And second, understanding the idea of a controlled operation, which is mechanism by which qubits are able to influence and interact with one another with a circuit. And I want to spend a good amount of time on this because in my experience the conceptual leap from single qubit thinking to multiple qubit thinking is where a lot of the real understanding either clicks into place or gets missed entirely. So let's take this slowly and carefully. Yeah. So let's begin with the fundamental question. So, what actual changes or conceptually when we move from talking about single qubit to talking about the system of multiple qubit? Yesterday we established that a single qubit state has to account for two possibilities, right? So the possibility of it being found in the state 0 and the possibility of it being found in the state 1, and that these two possibilities coexist with the qubit maintaining some combination of both until it is observed. So that gave us a relatively manageable picture to work with. And conceptually, one qubit, two possible outcomes, a combined state described the relationship between those two outcomes, right? So now when you bring a second qubit into the picture, something important happens here, right? There should be some difference happening here. So you don't simply have two separate single qubit descriptions sitting next to each other. Instead, the system as a whole must now account for every possible combination of outcomes across both the qubits simultaneously. So think about what that means conceptually. If each individual qubit has two possible outcomes on its own, then a pair of qubits together will be having how many possibilities? Absolutely. It is a four distinct possible combined outcomes, right? Because for every possible outcome of the first qubit, the second qubit could independently be in either of its own two possible outcomes. So this is a foundational idea and it's one that's easy to state. So but has like surprisingly deep implications because it means the amount of information required to fully describe a quantum system doesn't grow at a steady because predictable pace. As you add more qubits it grows explosively, right? So if you extend this reason further to 3 qubits, 4 qubits and beyond, you find that the number of the distinct combined outcomes doubles every single time you add one more qubit to the system, right? So this is what we refer to in theoretical terms as exponentially growth. Okay, and I want to emphasize why this matters so much beyond just being an interesting mathematical curiosity, because so this exponential growth is actually one of the central reasons why quantum computing is considered so powerful and simultaneously so difficult to simulate using ordinary classical computers. So a classical computer, no matter how powerful they are, has to keep track of every single one of these combined possibilities individually. If it wants to accurately simulate a quantum system, as you add more and more qubits, this bookkeeping burden grows so rapidly that even a modest number of qubits, somewhere in the range of 40 to 50, already produces a system so complex that no classical supercomputers currently in existence could feasibly simulate it in a full detail. And this is often referred to informally as the point where classical simulation becomes intractable. Okay, and now here is the conceptually important flip side of this. So a quantum computer doesn't have to simulate this complexity the way classical computer does, because the quantum computer it itself is a physical quantum system, right? And it naturally exists in the combined state, like multi-qubit state, as a matter of its own physical reality. So without needing of explicitly track or compute every individual possibility separately. So this is in essence the theoretical foundation for why quantum computers are believed to hold the potential advantage over classical computers for certain types of problems, not because they are simply faster in some generic sense, okay, but because the very information is represented and processed in is fundamentally different and scales differently as the size of the problem grows. And here I want you to sit with this the idea for a moment, because it's going to recur throughout the rest of this program in various forms. Okay, so every time we talk about adding more qubits to a system, we are not linearly adding more computational resources. Okay, so we are exponentially expanding the space of possibilities the systems can represent and explore simultaneously. This is the conceptual seed from which almost every claim about quantum computational advantage eventually grows. So let's now narrow our focus specifically to the two qubit case, since that's what we will be working with directly today, both conceptually as well as in our lab exercise. So when we have two qubits together, we said there are four distinct possible combined outcomes, right? That the system could be found in upon measurement. A general two qubit state before measurement exists as a some blended combination across all four of these possible outcomes simultaneously, not committed to any single one of them, right, but for holding some degree of presence across all the four conceptually speaking. Now, there is an important theoretical distinction I want to draw out here, and it's one of the most important ideas in this entire session. So, the distinction between qubits that are independent of one another and the qubits that are not. So, if two qubits are independent, meaning that whatever happens to one qubit has no bearing whatsoever on the other, then we can in principle always describe the joint behavior of the two qubits by separately describing each qubit on its own, and then combining those separate descriptions together in a systematic, well understood way. So this process of combining two independent description into a single joint description is referred to formally as a taking of tensor product, sometimes also called as a Kronecker product, right, in certain mathematical contexts. So I am mentioning the terminology here not to divide into the mathematical behind it, but because you will encounter this term repeatedly in the quantum computing literature. So, and it's worth being familiar with what is conceptually represents, and namely like the formal operations of the combining two separate qubits or independent quantum descriptions into one unified joint description. Okay, so however, and this is the crucial theoretical turning point, not every possible two qubit states can be broken back into two separate independent single qubit description in this way. So there exist two qubit states where no matter how you try to separate them, like you simply cannot express the joint state as coming from two independently described qubits combined together. So when this happens, we say that two qubits are entangled, right? So this is an extremely important conceptual marker, and I want to make sure it's crystal clear because it's going to become central to our discussion on the day three. So entanglement isn't some vague, okay, mysterious, some ideas that we invoke when things are getting complicated. It has very precise theoretical meaning. It refers to specifically to a situation where the joint description of two or more qubits cannot be decomposed into separate and independent description of each individual qubit. So, in other words, entangled qubits lose their individual identity in a very real theoretical sense. So, you literally cannot talk meaningfully about the state of qubit 1 or the state of qubit 2 separately anymore. And once they become entangled, you can only meaningfully talk about the state of the combined system as a whole thing. And today we are not at building entangled states, that's deliberately being held back for the day three, where we will explore it much greater depth and including how to create it and how to detect it and what it matters to so profoundly for quantum computing. But I want to introduce the this distinction now clearly and carefully because it directly sets up everything we are about to do with the C naught gate. Because as it turns out, the C naught gate combined with the certain other operations is precisely one of the tools used to move a system from being in that independent separable regime into the entangled regime. Okay, so today we will use the C naught gate in a slightly more limited way, without it triggering full entanglement. But understanding this broader context now will make day 3 land much more meaningful when we get there. Yeah. So now let's connect everything we have discussed conceptually to we are actually about to do hands on. Because I think this is where the theoretical ideas start to feel concrete, right? So we are going to work with a system of two qubits, and initially both qubits will simply sit in their default starting condition and a condition that conceptually represents completely certainly with no blending of the possibilities involved at all. Okay, and from there we will apply an operation to the first qubits, flip it, and we will get the output, and we will measure the output, and we will do the inspection based on the state vector. Okay, so without any delay we'll proceed with the hands-on session. Like if you guys have created the environment yesterday, okay, PPT was not visible. I didn't check that. Was it not visible to anyone?
Not visible.
Ma'am, I think like it is visible from my
It's
end.
visible. It's visible, Govardhan.
Okay, ma'am. Yeah,
It's visible.
thank you. Okay, can you check with the internet connections, ma'am? Ankush, sir, and all. Yeah. So, like, if you guys have created the environment yesterday, okay, so you know the procedures, right? You can just open the qBraid.com and you can launch the small instance. Okay, so I'll walk you through the steps slowly. If you have created the environment, no need to repeat the steps. Okay, so if you have created the environment, no need to repeat the step. If you have not, kindly follow my steps properly. If not, we will share the recording by end of the session. I think for day one deliverable it was little bit delayed, but for day two we will share it by the end of the session itself. Okay, so if everyone is on this page, kindly drop a message that we are in the Jupyter notebook, or you can give the thumbs up. If not, you can just drop in the chat like need some time.
Hello, ma'am. We are in same page. You can continue.
Okay, ma'am. Yeah, so once you are in this page, like if someone have missed creating the environment yesterday, kindly follow this step. Okay, so you can select the environment option here on the top right corner, and you can click on add option. Okay, once you have done that, you can click on create environment. Fine. Once you have done that, you can name your environment upon, like based upon your requirement. Give day 2 and so I'm just repeating it again. If you have created the environment yesterday, no need to like install it again and again, because you can just update the package and use the same environment, which will not utilize the storage system in the qBraid. Since it is a free trial, there will be limited storage for your accounts. Okay, so And in tag, you can give any keyword, and after typing it, kindly press the tab. Okay, so you can see that a key got generated. Once you have done that, then only you can create the sorry. So then only you can create the environment. So once you click on the create, wait for the packages getting installed. It will hardly take around a minute or a seconds. Okay. So once the like libraries are loaded, packages are loaded, kindly let me know. I'll tell you like about what are the other package you need to add for the day 2. Is it done? Tag, it can be any keyword, ma'am. Like I have given day 2. It can be any keyword, unique keyword describing about your package, sorry, environment. So that when you are selecting the environment, you will get to know like which environment you are choosing. Because if it is multiple environment, you will get confused like which one I created for this project and all. Okay, so now no need to worry, you can give anything. Okay, later when you're working on some projects using qBraid, that time you can give some unique descriptions or unique keywords.
Ma'am, I am getting a warning, ma'am.
Warning about what, ma'am?
Creation will fail if there are dependency conflicts.
uh, can you share your screen, ma'am?
Yes. Yeah, I think you can see my screen.
Actually, like, just a minute. Did you select on package? You did some changes for Python version one,
No.
like advanced customization. Did you? Yeah, you can just see. There is an drop down option, right? Yeah, you can just close that one for advanced customization.
But
So
create option is not getting enabled.
yeah, scroll down, ma'am. I'll tell you. Scroll up. Okay, just a minute. Hold on. Description. You have not given, ma'am.
Oh, that's mandatory.
Yeah.
Okay.
Yes. Okay. So, like people who have created the environment yesterday, no additional packages need to be involved here. Okay. So you can just keep the same environment. I'll tell you where, when and what you have to change. So okay, I'll just share my screen. Okay, so once the environment has got created, you can yeah. Here you can see more option, right? Next to your environment, click on that. And you need to scroll outside this and click on this add package. Okay. And then in search bar, you need to type the package name. Without clicking on add package, if you type it, you will not get the visibility of that package. Okay. So then you can type for Qiskit, the framework which we will use to build the quantum circuit. So, and then you can select the latest version. If you have already downloaded, no need to download it at all. Okay. But if you're creating it for the first time, the environment, then you need to download it. I will add in the comments what are the packages need to be downloaded. Qiskit for building using the frameworks, and for simulator we have Qiskit AER, and for visualization we need Matplotlib. You can just copy paste this exact keywords. Okay, no need to change the caps or small letters. Okay, everything is small only here. So once you have selected the version here, you need to click on add so that that package will get added to your environment. Okay, repeat the same procedure for all the 3 packages which I have shared in the comment box. Is everything set? Is it done? Shall we move to the next step? Okay, I guess everyone's is done. Okay, so once you have added this package, right, you can go to the folder which you have created yesterday. Inside 5 days FDP, you can create another new folder. This one, everyone can follow this step. Another folder. Why I am creating these folders? Because to just keep it structured. Okay, so you can create day 2 folder, and inside this, you can create new. Okay, you can right click, you can see this new notebook, right? You can create that. And if you give control S, or you can just go here and you can give the rename also. Okay, so here you can give 2 qubit. So yesterday we didn't have enough time to program it on your own. Today we will be doing the programs by line execution. Okay, so once we finish this one, we can go for a short break and continue with the C0 gate operation. So first, let's verify whether we have created the 2 qubit system or not. Okay, so everyone create this IPYNB file by right clicking on this folder and create new notebook and name it as the file you want. And you need to open it also. Okay, so once that is done, here you can change the kernel. So the one who have created the kernels yesterday, you can just select that kernel. The one who have created the kernels today, you need to select that kernel. Okay, that specific kernel here, and click on the select option. So once you have selected the kernel, you can just click on this restart kernel. Whenever you are changing the kernel or updating the packages, or you are newly launching this instance, then you need to restart the kernel every time. Okay. Okay, so let's start by typing our very first import. Okay, so this line brings Just a minute. Yeah, so this line brings in the quantum circuit class from qSCADE library. So this is the fundamental building block we will be using throughout this entire program. So every single circuit we construct, whether it involves 1 qubit or 10 qubits, start by creating an object using this quantum circuit class. So think of this input as bringing in the tool that lets us actually define the structure of quantum circuit. So which qubit exists and what operations get applied to them. Okay, so you can go ahead and type the line now, that is from this kit we can import the quantum circuit. Okay, so next we import AER. That is, AER is qSCADE simulator package. It's what allows us to run our program like quantum circuits on a classical simulator rather than on actual quantum hardware. So since we don't here we are not for the basic experiments, we are not going to work on physical quantum hardwares. For Bell circuit on the day 3, we will be working on the real quantum hardwares. Okay, sitting in front of us, and everything we run in this program will be executed on a simulator, and AER is the component that provides the capability. So it's worth understanding that a simulator behaves for our learning purposes like exactly as real quantum hardware would. So it follows the same rules, produces the same kinds of outcomes. The only difference is that it's running on the classical computing infrastructure rather than the actual quantum processor. Okay, so you can go ahead and type the line from qSCADE ER. You can import ER. Okay, and now we import state vector. So this is particularly important import for today's session because it's going to let us do something we didn't do yesterday, like inspect the exact internal conditions of our qubits before any measurements takes place. So yesterday we only looked at measurements outcomes, the classical zeros and ones that come out at very end. So the state vector lets us pause before a final measurement step and look directly at the fully underlying description of a qubit's condition. So this is extremely useful tool for learning and verification purposes because it lets us confirm our circuit is doing exactly what we expect before we even get to the measurement. So you can type the line now from qSCADE dot quantum info. You can import state vector. Okay, so once this is done, now we are going to import, which brings an visualization tool called plot histogram. So we used this yesterday as well. It's what allows us to take the raw output counts from a measurement and turn them into a clear visual bar chart. Okay, and we won't use this immediately in this particular lab since we are starting with the state vector inspection rather than the measurement, but we will need it a little late today when we move to the lab 8. So we are importing it now to keep all our inputs together in one place. So you can go ahead and type from skit visualization and import plot histogram. Okay. So next line imports the matplotlib, so which is a general purpose plotting library. So plot histogram actually relies on matplotlib, right, behind the scenes. So to render its chart, so we need this import available for our visualization to display correctly. So you can go ahead and type import function for matplot library. And import it as PLT. So wherever you are going to use matplotlib, you can use the keyword as PLT. Okay. So now on this line, we are creating something called as a backend. Okay. So a backend conceptually represents the actual computational engine that will execute our circuit once we are ready to run it. And here we are specifically selecting the AER simulator backend, which is the general purpose simulator we discussed a moment ago. So every time we want to actually execute a circuit later in the program, meaning like run it and collect measurement outcomes, we are going to refer back to this backend variable. So this line is essentially uh, a setting is it is essential for us to set up once the simulator we will be running everything on the throughout this today session. So you can type that line now, and once everyone has it typed in, and go ahead and run this cell. Okay. So you can define the backend into the variable AR at backend. Okay, so once you have done everything, like have typed all the programs, you can just click on Control Enter so that your cell will get run. Okay, and you will know if you are not getting any errors, it is well and good. If you are getting errors, you would have missed some package or some keywords. So kindly be careful while typing the package's name. It is a case sensitive also. So anyone facing issues? Way to select AER, like in the packages, ma'am. Yeah, same procedure. So you can go to click on more, and first you need to select add a package, and then you need to type Qiskit AER. So you will get that package and download the latest version available. And after you have selected that, you need to click on this add button so that that package will get added. Once you have added that package, kindly restart your kernel. So first you need to select the kernel which you have used. Okay, and then you need to select it and restart the kernel and run the program. Ma'am, did you download matplotlib library? Ma'am, actually, it is not from ma'am. It is importing. We are importing matplotlib library directly. We are not using some other package to import the matplotlib. Okay, we are directly importing the package, and we are naming that as giving it as a surname, like alias name, that is PLT. So instead of using this lengthy matplotlib.pyplot, we are going to use it as PLT. So the program is, you need to, instead of from, you need to type import. Yeah. So once you type import, you can just run the cell and check it. Okay, I think like everyone have worked on it. Is it fine now? Or anyone facing any issues? Okay, so this completes our first setup, and every lab we do for the rest of today's is going to build directly on top of these pipelines. Okay, so it's worth having them clearly in place before we move forward. So in the next cell, if you are not getting next cell, you can just click on add down cell, insert a cell below, or you can just shift enter. If you give, new cell will get created. Okay, so once you are in the new cell, you can now we can move to next cell, so where we will actually build our first 2-qubit circuit. So on this line we are creating a new quantum circuit object, and we are specifying that it should contain 2 qubits. That's what the number 2 inside the parenthesis will be representing, and we are storing this circuit inside a variable called as qc underscore sv. Okay, I will name it in this way specifically to indicate that we are going to use this uh, circuit for state vector inspections. Okay, and which is exactly what we are about to do now. And at this point, both of our qubits will be sitting in their default starting condition, so nothing has been applied to them yet. You can just create a variable qc underscore sv. Can type the quantum circuit. Okay, ma'am, can you share your screen? Snehal, ma'am, can you share your screen so that I can check where your issue is coming from the package, whether it is installed correctly or not? Yeah. Ma'am, actually, you have not selected the kernel. Can you see that Python? Sorry, ma'am. Yeah. So be on this page itself. You don't need to navigate back. Okay. So yeah, go to that. And on top, you can see that Python 3 IPY kernel. Yeah. Click on that. Click on this drop down. Select the, yes, you can select that one. This is the one you created today, right? Yeah, you can click on select. And there is an restart option here. Can you see on the top? Yeah, restart it. And now try to run it, ma'am. No, a restart once is enough. You can just run the cell. Okay, still you're getting this error. Okay, ma'am. Can you minimize the screen on the right side? This one, like Google Meet one. Yeah, you can click on into. Close the tab. Yeah. Can you close this? No, no, no. Yes, ma'am. Close that one. There is a close mark here. Can you see on the top right? Not in this one. On the right side. Yeah. So can you click on this more? Yeah. So can you go to add package first? Down. Come out of this box and yeah, click on that. And can you type Qiskit? Okay, it have been installed. iPhone, not underscore, ma'am. iPhone, AER. Yeah. Can you select that? Add package. Yeah, already installed. Okay, fine, good. And next, matplotlib. First, you need to type the add a package. Okay, it is also installed. Okay. What is the issue? Okay, can you go back, ma'am? Let me check with the code. Is there any mistake in that? Yes. Ma'am, can you see this Qiskit underscore visualization? It is Qiskit dot visualization. The fourth line. Yeah. You can just remove the underscore and keep it as dot. Yeah. Mm. Okay. Yeah. Okay. After get, there should be an underscore, ma'am. AER dot get backend. Yeah. Underscore. Yeah. Okay. You can stop sharing the screen. No issues. Yeah. Okay. So let's resume it now. Okay, now we can resume with this one. So here we have created one variable and we have stored the 2 qubit circuit inside this variable. So whenever we are working on some operation on this, we can just call this variable itself. Okay, and next line, that is where I'll be calling this variable and I'm going to, yeah. So on this line, we are applying an operation to the qubit 0 specifically. Note that 0 inside this parenthesis, okay? So which tells the circuit exactly which qubit this operation should act on. And the operation itself referred to here as the X. So is what flips a qubit away from its default starting condition into the alternative condition. So after this line executes, qubit 0 will no longer be in its original condition. So it will have been flipped. Like qubit 1, meanwhile, remains completely untouched at this point since we haven't applied anything to it yet. So I want you to notice something as you type this. We are deliberately setting up qubit 0 to be in a definite flipped condition before we bring qubit 1 into the picture at all. Okay, so this is intentional and it directly sets up what we are about to do in the next line. So you can go ahead and type this line. So now here is what the most conceptually important step. Okay, so the line in this entire cell, this line applies our controlled operation, the one we spent considerably time discussing conceptually just before the lab began. So you can notice that the two numbers, that is like if I'm going to give dot cx and I'm going to give 0 comma 1. So inside the parentheses, we have two numbers, that is 0 and 1. So the first number specifies which qubit is acting as the control bit, and the second number specifies which bit is going to act as the target bit. So in this case, qubit 0 is our control and qubit 1 is our target. So as we discussed, the entire behavior of these operations depends on the current condition of the control bit. Since we already flipped qubit 0 on this previous line, our controlled qubit is currently in its flipped condition. Because of that, this operation will also get flipped by our target qubit, and qubit 1 purely as a consequence of the controlled qubit's current condition. So had we skipped the previous line and left qubit like 0 in its original default condition, these same operations would have left qubit 1 completely undisturbed. So this single line is really where the conceptual idea of controlled operation becomes concrete. Like you can just go ahead and type this line for applying the C naught gate. Okay, so in the C naught gate, there will be two qubits. C naught gate cannot be applied on the single qubit because we are having only one qubit there. So for C naught gate, you need to have two qubits. That is, one will be acting as the flipping a qubit and another one will be acting as the target qubit. Installation failed. Ma'am, can you share your screen? Let me check it. Yeah, you need to click on the add package. Yeah, now you can. Ma'am, you need to select the version, ma'am. You're not selecting the version. Type the matplotlib. First click on add package. Yeah, now type it. Yeah, there you can see any option, right? Click on that drop down. Yeah, select the latest one, 3.11.1. Now you click on the add. Yeah, so now you can restart the kernel and work on the program. Okay, so and finally we are on this last line. Okay, so that is state vector word from. So we are using the state vector tool we imported earlier to inspect the exact internal condition of our entire circuit. So as it stands right now. And after both of the operations we just applied, but importantly before any measurements have taken place. So this line doesn't modify our circuit in any way. It simply lets us look into inside it. and see precisely what condition our two qubits are collectively in. So you can type that line now and then go ahead and run this entire cell. Yeah. So once you run it, you should be seeing an output describing the combined condition of your two qubit system. So what you're looking at in that output is a direct confirmation of everything we discussed conceptually, because we deliberately flipped our controlled bit before applying the controlled operation. So both of our qubits should now show up as a having moved into their flipped conditions together, so with complete certainty and no ambiguity involved. If your output matches the expectations, it means your controlled operations behaved exactly the way we described in our conceptual discussions a few minutes ago. Okay, so everyone, if you have executed till here and is not facing any issues, we'll take a short break and you can get back by 3:30, so we can resume with C naught gate implementation and we can visualize it using the bar graphs also. Okay, so I hope you got a chance to stretch and refresh a little. So, before the break, we spent our time understanding controlled operations conceptually, and we saw our very first hands on example of it through state vector inspection, right? And in the second half, we are going to build directly on that foundation where we will formalize it properly into the C naught gate and then move into our final hands on lab of the day where we will actually observe correlations between the qubits ourselves. Okay, so let's begin this session by turning our attention to a new theme like quantum correlations. So everything we do for the remainder of today is going to build toward understanding what it means for two qubits to be correlated with one another and why that correlation matters to significantly in quantum computing. So, what are quantum correlations? So, let's start by asking, like, in a very careful and precise way. So, what we actually mean when we say two qubits are correlated. So, when two qubits are made to interact with one another, for instance, uh, through the kind of controlled operations we discussed before the break, right? So something important happens to their measurement outcomes. Specifically, the outcome you get when you measure one qubit is no longer independent of the outcome you get when you measure the other. So, in other words, if you know what one qubit measured, you gain information about what the other qubit is likely to measure as well. So, this linking of outcome is what we refer to as a correlation. And now it's important to understand that correlation itself is not a uniquely quantum idea, and correlation exists in classical systems too. So consider a situation where two objects were deliberately prepared ahead of time, so to always agree with one another, and were the separate like then separated. Even after separation, observing one would immediately tell you the state of the other. But this kind of correlation was, in a sense, deciding decided in advance before the objects were ever separated. So, this is what we refer as a classical correlation, a form of correlation that could, in principle, always be explained by some prior agreement or share history between the two systems. Okay, so quantum correlation is fundamentally different and considerably stronger in the quantum case. So the correlation between two qubits can exceed anything that could possibly be explained by any kind of prior agreement or shared classical history. So this is precisely the foundation on which entanglement is built, and it's one of the reasons entanglement is considered such as like profound department from the classical physics. For today, our lab work is going to focus specifically on the correlation that emerged from the basic two qubit circuits using tools we already understand, particularly the C naught gate. So we are deliberately not yet diving into the full depth of the entanglement itself, since that's reserved for tomorrow, that is day 3, where we will study it formally and rigorously. Okay, so yeah, let's now formalize in precise theoretical terms the idea of the controlled operation. So since this is going to be central to everything else we do today, a controlled operation is defined by a very specific rule. It acts on what we call a target qubit, but only under one particular condition. So that a separate qubit, which we call the controlled qubit, is currently found in the particular condition. If the control qubit is not in the condition, the target qubit is left completely untouched, exactly as it was before. So this general structure is often referred to in the broader theoretical language of the quantum computing as a controlled U operation. So where U simply stands in for whatever specific operation we intend to conditionally apply. So the governing rule is straightforward and worth repeating carefully. So if the controlled qubit is found in its default condition, the target remains entirely unchanged. If, however, the controlled qubit has been shifted into its alternative condition, then the specified operation is applied to the target qubit also. So now I want to draw out why this idea matters so significantly beyond just being a piece of circuit notation, because the controlled operations are quite literally the mechanism by which qubits stop behaving as isolated, because independent entities and begin to interact with and depend upon one another. So without controlled operations, every qubit in a circuit would evolve entirely on its own, with no relationship whatsoever to any other qubits in the system. So it is specifically through controlled operations that correlations between the qubits are introduced. And this idea extends even further. controlled operations are not just a tool for creating correlations in a narrow sense, they are fundamentally the building blocks that underlies entanglement itself, and they appear as a core component in the vast majority of the multi-qubit algorithm used throughout quantum computing, so well beyond just the simple example we have working through today. Let's now take this general idea of the controlled qubit controlled operation and apply it one on a very specific and extremely important example. Okay, so the C naught gate, which stands for control not gate, and this C naught gate is widely regarded as the simplest possible two qubit gate, and yet despite that simplicity, it's also considered the single most important two qubit gate in this entire field. So, structurally, it involves exactly two qubits playing two distinct roles, and one qubit serves as the control, and the other serves as the target. The governing rule of this CNOT is very precise and worth stating carefully. So, if the controlled qubit is found in the alternative condition, the target qubits gets flipped away from whatever condition it was previously in. If the controlled qubit remains in its default condition, the target qubit is left completely undisturbed. And there are two additional theoretical properties of this CNOT gate that that are worth understanding clearly. So first, the CNOT gate is reversible. If you apply it twice in the succession under the same control and target assignment, the system returns exactly to whatever condition it was in before gate was first applied. And this reversibility is actually a general property shared by all the valid quantum operations, not just C naught specifically. But it's good, like concrete place to first encounter this idea. Second property is that this is a particular significant theoretical result. So the CNOT gate, when combined together with a appropriate set of single qubit operations, is sufficient to construct absolutely any quantum circuit whatsoever, no matter how complex. This property is referred to as forming a universal gate set. In practical terms, this means that no matter how sophisticated a quantum algorithm you might eventually study, whether it's used in cryptography or optimizations or simulations, it can be in principle be broken down into nothing more than a single qubit operations and repeated applications of the CNOT gate. So this is precisely why the CNOT gate receives so much attention early in any quantum computing curriculum. Now let's look at this behavior laid out in a complete systematic way, covering very possible starting condition. So what you are looking at here is a complete enumeration of every possible combination of controlled and target conditions. So along with the resulting conditions of the target after the CNOT gate has been applied, walking through this carefully, when the control is in the default condition, the target remains exactly as it started. So, regardless of what conditions the target itself was in, this confirms in both possible target scenarios that an untouched control leaves the target completely unaffected. However, once the control shift into its alternative condition, the behavior changes entirely. So, in both possible starting conditions for the target's final conditions is now flipped away from the whatever it started. So, this table taken as a whole and is really just the formal, complete statement of the single governing rule we discussed a moment ago. The control qubit is never altered by this gate under any circumstance, and the target qubit only flips when the control happens to be in the alternative conditions. So I want to briefly mention that this same behavior can also be captured using a formal mathematical representations. Though I won't well into the mathematics itself in detail. What's conceptually important to take away here is that this representation is simply another way of encoding the exact same rule we have already discussed. Like under this formal representation, you will notice that two of the four possible combined conditions get exchanged with one another, right? So while the remaining two are left completely undisturbed. So this exchange precisely correspond to the situation where the control is in the alternative condition, causing that target to flip. So while the untouched condition, sorry, so while the untouched condition correspond exactly to the situation where the control remains in a default condition. So even at this more formal level, everything remains fully consistent with the theoretical rule we built up earlier. Yeah. Now, let's move into the final hands on exercise for today. And the objective of this lab is to construct some simple 2 qubit circuit using exactly the tool we have just spent time discussing conceptually, and to directly observe through actual measurement outcome the correlation that emerge between our 2 qubits. Here's the overall structure we will be walking through. So we are going to build a circuit involving an initial operation on 1 qubit, followed by a CNOT gate linking that qubit to a second qubit, and then measure both qubits and record the resulting outcome counts. Once we have done that, we will deliberately repeat the exercise with a slight modifications, removing that initial operations so that we can directly compare how the presence or absence of that first step changes the correlation pattern we observe. We will also try reversing which qubit plays the role of control and which plays the role of target to observe how the affects the outcome. And throughout, we will be paying the close attention to a specific question, which combined outcomes actually appear in our results, and just as importantly, which combined outcome never appear at all. All right. So with that structure in mind, let's move into the hands-on now and go ahead and start building this practically. You can resume your qBraid account. Okay, if it have got shut down, no issues. You can just close the tab and you can relaunch the tab here. If you don't have this option, you can just click on launch small instance one. Okay. Yeah. So you can just click on launch. Okay. So you can open your file here and make sure to select the kernel. If it is not selected, you can just go and select the kernel which you have created for your project, and make sure to restart the kernel. Okay, once it is done, make sure to run this import function, because if you are going to use the package from this, you need to run this. That is what the like how the Jupyter notebook works, right? and later you can create a new cell. Fine. So here what we are going to do is we are going to create a new quantum circuit, and this time notice that we are specifying two separate numbers. So when we create it, and the first number tells the circuit how many qubits that it contains, and the second number tells the circuit how many classical bits it should reserve for storing the measurement outcomes. Since we intend to measure both of our qubits this time, so we need two classical bits available to store those two separate results. Okay, so we'll type this now. That is QC is equals to quantum circuit. No, 2 comma 2. Okay, next what I'm going to do is just as we did before the break, like we are going to apply an operation to the qubit 0 that flips it away from its default condition. So this sets up our controlled qubit in a definite known condition before we bring the second qubit into the interaction. Okay, so next we will apply our controlled operation with qubit 0 acting as the control and qubit 1 acting as the target. So based on everything we just discussed conceptually, since our control qubit has already been flipped, we should expect the target qubit to flip as well, right, as a direct consequence. You can type qc dot. Okay, now what I'm going to type, this line is new compared to what we did before the break. Here we are explicitly instructing the circuit to measure both of our qubits and store their outcomes in our two classical bits. So the first list identifies which qubits we want to measure, and the second list identifies which classical bit each corresponding measurement outcome should be stored into.
Ma'am, excuse me.
Yes, ma'am.
Can you zoom it a little?
Yeah, sure.
Yes. Okay.
Is it okay, ma'am?
Yeah, ma'am. Now it is visible.
Okay.
Yes, sir.
Okay. So now on a fresh line, we are going to actually execute this circuit, and we are using the backend we set up earlier in the day. And we are specifically that we want this circuit run a large number of times, repeated many times over, so that we can build up a reliable picture of outcome pattern rather than relying on the result of any single run, right? And finally, on this last line, we take the outcome counts from our results and pass them into our histogram plotting tool, so that we can get a clear visual representation of exactly which combined outcomes occurred and how frequently each one occurred across our represented, like repeated runs. Now you can go ahead and run this cell. Make sure to run the import cell first and then you need to run this one. Or else all the packages will not get imported because you have restarted the kernel. Okay, is everyone on the same page or anyone facing issues? Subodh Kumar sir, okay. If you have missed it, also no issues. We have shared the recorded video, okay, about qBraid of yesterday's session, where you will get the steps involving how to create the labs and how to set up the environment. And source codes are also being shared in the deliverables only. So no need to worry about. You can execute it. If you are facing any issues, kindly let me know in the next session or today also. If you have already started working on it, you can just let me know. Anyone stuck in the current cell or you guys facing any issues? Okay, now take a look at your resulting histogram. Okay, so based on everything we discussed conceptually, you should be seeing a single dominant outcome appearing consistently, like both qubits ending up in the same flipped condition together. So essentially every single time across all of your repeated runs. So this is a very direct visual confirmation of the correlation we have been building towards conceptually. And the two qubits are not behaving independently of one another at all. So their outcomes are moving together consistently as a direct consequence of the controlled operations we applied between them. And I would now encourage you to try the two variations we discussed. Like first, repeat these circuits without that initial flip on the qubit 0, and separately, like try reversing which qubit acts as the control and which acts as the target, and compare what changes in each case. You can try it after this session also. Does anyone have doubt till this hands on? Okay, fine. So let's now pause and open this up as a quiz. Okay, so you can drop your answers in the chat box. So in a C not gate, if the control qubit is 0 and the target qubit is 1, so what is the target qubit after the gate has been applied? You can drop your answers inside the chat box. Yes, absolutely. It is so correct. Why? Because when target bit is, oh, sorry. So, yes, any other answers? Okay. So I think, yeah, Archana ma'am have answered the correct answer. Yes, because target is unchanged when the control bit is 0, right? Because if the initial stage is not at all flipped, means the target bit will not get flipped. If there is any flipping of the bit occurs, that time your target bit will get flipped to the next stage when you are applying the gates. I think everyone's energy has gone down after repeated theory sessions and hands on. Okay. Only just last two questions I'll be asking. So no need to worry. After that, we can wind up the session. Okay. So yeah. Uh, we'll have a quick discussion about it, like you can share your thoughts on this. So I want everyone to take a few minutes to really think this through, and then go ahead and drop your thoughts directly into the chat box. I'll be reading through your responses. So here is the central question I want you to sit with. So why is it that a single control qubit is able to determine the fate of the another qubit, even though the two qubits were never entangled with one another beforehand? And to help you think this through, consider these related angles, as well as, is the C naught gate itself actually creating entanglement in this particular scenario, or is it doing something more limited, simply applying a condition flip? So, what do you think would change if, instead of starting any definite conditions, our control qubit had been placed into a blended conditions beforehand? And finally, when where in the classical digital logic have you previously encountered a small control target style of relationship? You can go ahead and take a few minutes to think this through and discuss among yourself, and drop your thoughts in the chat box now. I'm not getting any answers. Like, did you guys really understood the concepts for today, or is it causing any difficulties in understanding concepts? Should I move even more slow? You can open up or share your feedback so that I can like we can go with even more smoother in the next session. Okay, so no one is answering. I'll be only answering it. So the most precise way to think about this is that like in a specific scenario, and I want to offer my own perspective on this, like trying together the different viewpoints. The most precise way to think about this is that the specific scenario we just ran, right? The C naught gate is not creating entanglement, but because our control qubit started out in a completely definite certain conditions with no blending of possibilities involved at all, right? And entanglement as well, as we discussed earlier, only becomes relevant when we are dealing with the combined conditions that cannot be broken back down into separate independent, right? In a principle still describe each qubit's conditions individually even after the C naught gate was the applied. So there was never a point where the two qubits became inseparably linked in a former sense. So what we are really observing here is best described as a conditional flip in the, not the entanglement. Okay, so here whatever the thing we are observing is entirely is about flipping the gates. So that's it. This exercise sets up something extremely important for tomorrow. So if our control qubit had instead been placed into a blended conditions before the CNOT gate was applied, the outcome would have been fundamentally different. Like, and that specific scenario is precisely what leads us directly into the genius, entanglement will be created. So you will be seeing it in the tomorrow session how CNOT will play major role in creating the Bell state, that is the entanglement state between the two qubits. Okay, if not about the discussion, at least answer for the final quiz, at least. Okay, so let's now put this understanding to the test with a quick quiz question. Take a moment to read through it carefully, and once you have settled on an answer, go ahead and drop your choice, just the option letter in the chat box. Let me read this question for you. So here's the scenario. A circuit applies an operation to the qubit 0 and that places it into a blended condition. Then applies a CNOT gate with the qubit 0 as controlled and qubit. So one as the target and finally measures both the qubits. So the question is, which combined outcomes are possible here? You can take a moment now and think it through carefully and drop your answers in the chat box. You can just drop the option. Okay, I think only Archana ma'am is active. She had coffee, I guess. Everyone is sleeping. Okay, Ranjita ma'am, I got another vote. Anyone else woke? Guys, from tomorrow's session, you can keep your coffee ready by your side so that during the breaks, you guys can have a coffee and wake yourself up and cheer yourself to learn for the session. I think tomorrow it will be even more interesting because it is a even more complex circuit than the 2 qubit, which is a Bell state one. I am so eager to teach you guys about it because tomorrow we are not just going to sit and run it on the simulator. We will work on the actual real quantum computers. I think you guys are excited about running it on quantum computers, right? Yeah. Thank you, ma'am. Okay, all right. The let's go through this together. Okay, for this, the correct option is C. Why? Because only two specific combined outcomes are possible and they occur roughly equally often, right? And each close to about half the time. And here's the reasoning behind why this is correct. Because our control qubit started in a blended condition rather than a definite one, so it doesn't commit to begin in its default or alternative conditions until measurements actually occurs. So but whichever condition it does end up being measured in, the CNOT gate ensures that the target qubit ends up matching the same condition precisely because of the controlled operation we discussed at length today. And this means the two qubits are forced to agree with one another in every single measurement outcome. So you will never see a result where the two qubits disagree with each other, right? And because the initial blended condition was an even split between the two possibilities, both of the matching combined outcomes should occur with roughly equal frequency across many repeated runs. So this particular circuit, by the way, is genuinely significant. It's precisely the circuit that produces what's known as a Bell state. So, which is exactly what we will formally study in the later class. Okay, let's take a moment to consolidate everything we have built up across today's entire session. Okay, so we learned the multi-qubit systems require an exponentially growing amount of information to describe fully as the number of qubits increase. And we understood that controlled operations are the mechanism through which one qubit is able to influence the another, and that this forms the basics of the interactions between qubits in any quantum circuit. And we studied the C0 gate specifically is considered depth, understanding its governing rule, its reversibility, and its roles as part of a universal gate set capable of constructing any quantum circuit whatsoever. And in our lab work today, we directly observed through actual measurement outcomes how two qubit circuits can already produce meaningful correlations between qubits even before we have formally introduced entanglement. So tomorrow on day 3 we take the natural next step. So we move from the correlations into the formal rigorous study of the Bell states and entanglement itself. Yeah. So that brings us to the end of today's technical content, and with that, we also wrap up day 2 of our FDP. And before we close, I would like to open the floor for any remaining questions you might have about controlled operations, the CNOT gate, and the correlations we observed in the lab gate, or anything else from today's sessions. Please feel free to type your questions in the chat box. I'll be addressing it. Okay, I want to sincerely thank all of you for your engagement and participations today. And the discussions were thoughtful. The quiz response was limited. I hope everyone will get their coffee tomorrow. And yeah, so with that, we conclude day two of our program. Tomorrow, we move into bell states and entanglement, where a lot of what we have built conceptually today is going to come together in a very satisfying way. Okay, so I see you. I want this. I don't want the same energy, a little bit with high, more energy will be required for tomorrow's sessions. So thank you all once again for your time and energy today. And I look forward to contributing this journey with you tomorrow. Have a wonderful rest of your day. That's completely okay. Most people find this concept difficult when they first hear about it. So by the end of the today's session, my goal is that every one of you should be able to explain it in a simple and confident way. So let's begin then. Yeah. So before learning something new, let's quick revisit what we learned yesterday because today's topic builds directly on those concepts. So this slide should sound like you are giving the now you can recall about what are the concepts you have learned yesterday, right? So now that we have officially started today's session, let me give you a quick overview of what we are going to cover over the next few hours. So I always like to begin with the agenda because it helps everyone understand what we are heading and how today's concepts are connected, right? So as you can see on the screen, today's sessions has four major parts. So each part built on the previous one. So by the end of the session, you will have both the theoretical and understanding and practical experience. So let's go through one by one. First, we will begin with understanding the basic concepts. Like before writing any code, it's important to know what we are trying to achieve, right? So we will answer questions like what exactly a bill state is, why it is called as bill state, what is entanglement, why is entanglement considered one of the most important features of the quantum computing. So many people hear the word entanglement and think it's something very difficult, but today I'll explain it using simple examples so that everyone can understand it easily. Okay. Next, once we understand the theory, we will immediately move to the practical session in the lab 9. So we will create our first Bell state using the qBraid platform. Instead of simply copying the code, we will build the circuit step by step. Okay, for every line of code, I'll explain what we are writing, why we are writing it, and what happens inside the quantum circuit after that line executes. And we will also observe the quantum state before the measurement and then execute the circuit to the measurement results. So this way you will understand not only how to create the Bell state but also why each gate is required. And after creating the Bell state, an important question comes up, right? How do we know the qubits are actually entangled? Can we prove it? Right? That's exactly what we will discuss in the next session. We will understand how measurements helps us verify entanglement. Okay, and we will analyze the outputs carefully and see why only certain measurements results appears. So this is where the theory starts making practical sense. Finally, we will perform another hands-on activity. We will analyze the relationship between the two qubits after the measurement. And you will notice something increasing. Whenever one qubit is measured, the other qubit's result is closely related, and we will study these correlations and understand why Bell states behave differently from two independent qubits. And these experiments will help you visualize what entanglement actually looks like through the measurement outcomes. So if I summarize today's journey, it will look like this. Like first we will understand the concept, then we will implement it. Next we will verify whether our implementation is correct. Finally we will analyze the result and understand the behavior of entangled qubits.
Govardhani, you are muted, I think. Hello.
Yeah, thank you, ma'am. Sorry.
Okay.
Okay, no issues. So, if I summarize today's journey, it will be looking like this. First, we will understand the concept, then, we will implement it. Next, we will verify whether our implementation is correct or not. And finally, we will analyze the result and understand the behavior of entangled qubit. So, today's session is not just about learning a new concept, it's about understanding it and implementing it, verifying it, and analyzing it. Okay. Yeah. Now that you know today's roadmap, before we learn something new, let's spend a few minutes revisiting what we learned yesterday. So today's topic is actually built on yesterday's concepts. Okay. So a quick recap will help us connect everything together. So let's move to the day two recap. So before we start, like in quantum computing, every topic builds on the previous one, right? So if we clearly remember yesterday's concepts, today's topic will become much more easier to understand. So yesterday we moved beyond single qubit system and started working with multiple qubits. Until then we had mainly focused on understanding how one qubit behaves, how it can be in a state of 0 1 or a superposition of both. But in real quantum computers we rarely work with just one qubit, and most useful quantum algorithms require multiple qubits working together, right? So yesterday we created our first 2 qubit circuit and learned that once we have more than one qubit, something interesting happens. So the qubits are no longer completely independent. We can make one qubit influence the another using the controlled operations. So that was our first step towards understanding quantum system. Next, one of the most important gate we learned yesterday was the control NOT gate, also called as C NOT gate. So let's quick remember how it works. The C NOT gate have two qubits, and one is called the control qubit and the other is called the target qubit. And the controlled qubit decides whether any action should happen or not, and the target qubit is the one that may change based on the controlled qubit's action. Now here's the important rule: the target qubit changes only when the controlled qubit is in the state of 1. If the control qubit is 0, nothing happens. If the control qubit is 1, the target qubit will get flipped. So that simple rule is what makes the C0 gate different from the gates we studied earlier. Okay, and yesterday we also observed something interesting, right? So when we measured 2 qubits after running certain circuits, we started seeing relationships between their measurement results. So instead of looking at 1 qubit by itself, we began looking at both the qubits together. Like something, the result of 1 qubit gave us the information about the other qubit. So at that stage we simply observed these measurement patterns, so we did not give them a specific like special name yet. Today we will understand why those patterns happens. Now think about what we already know. We know how to create a superposition using the Hadamard gate, and we know how to create C0 gate. We know how the C0 gate works. Today we are going to combine these two ideas. We will first create the superposition using the Hadamard gate, and then we will apply the C0 gate. Okay, just these two operations are enough to create one of the most famous quantum state, that is the Bell states. And once we create a Bell state, something very special happens, that is the 2 qubits will become entangled. So this is not just another quantum circuit, it is one of the most important circuits in the quantum computing, because many advanced applications begin with this exact circuit. For example, quantum teleportation, superdense coding, and cryptography, as well as quantum communication, many quantum algorithms, all these make use of the entanglement in one way or the another. So today's session is actually a continuation of everything we have learned so far. And we are not learning something completely new, we are simply building on the concepts we already understand. So now that we have refreshed our memory, let's officially begin with the today's topic. So we will start with the simple question. So what exactly is the Bell state and why is it so important in the quantum computing? Okay, so from this point onward, we will focus on understanding Bell state and the idea of the entanglement. So in engineering, it's always better to understand the concepts first and implement it later, right? So if we directly start coding without knowing why we are doing something, it because it becomes difficult to remember later. So today's objective is very simple: by the end of this concept session, you should be able to answer the questions like what is Bell state, what is entanglement, why is it considered one of the most important discoveries in quantum computing. Okay, so let's start with the name itself. What is a Bell state, right? So a Bell state is a special quantum state involving 2 qubits. Notice that I said 2 qubits. Like a Bell state cannot exist with only 1 qubit. We need 2 qubits because the entire idea of entanglement is about creating a relationship between the two quantum particles. Okay, so the slide says Bell state are four special 2 qubits, right? And states that shows maximal entanglement, which means imagine two students writing an exam. Okay, normally each student writes independently. One student's answer doesn't affect the other student's answers, right? But similarly in classical computing, if we have 2 bits, each bit behave independently. One bit doesn't know what the other bit is doing. But in quantum computing, we can create a situation where 2 qubits behave like a team instead of behaving independently. Okay, so that special relationship is called entanglement. Among all possible entangled states, there are four very important nodes. These are called as Bell states. So they are named after the physicists like John Stewart Bell, who studied how quantum systems behave differently from the classical system. Now let's look at the mathematical expression mentioned here. We have 5 plus, right, range is equals a range of fraction of 0 0, range plus 11 range of square root of 2 means. Now don't worry if this equation looks unfamiliar, we will understand it step by step. Let's look at the 0 0 state. Okay, this simply means first qubit is 0 and second qubit is also 0. So similarly in the 1 1 state also. Okay, so here the first qubit is 1 and the second qubit is 1. Now notice something interesting. Do you see the state of 0 1 anywhere? No. And 1 0 anywhere? No. Why? Because only 0 0 and 1 1 are the present one. So that means before measurement the system is in a superposition of these two possibilities. When we measure something we will get 0 0 and sometimes 1 1, but we will never get the answer of 0 1 or 1 0. So we will actually verify this during our today's lab. And yeah, so can I ask you some questions like which measurement results do you think are possible from the equation, whether it will be 0 0 or 1 1 or 0 1 or 1 0? Exactly, what will happen when we are executing some circuits? Okay, I think like during screen recording, I can't navigate it back. It's fine. You can drop your answers in the chat box. Whether like after executing the bell state, what are the states will be present when we do the measurements. So you can drop it in the chat box. I'll check it in the later session. Okay, once I have finished my slides. Okay, now comes an interesting question. How do we actually create the bell state, right? So, do we need any 10 gates or 20 gates, a very complicated circuit? No. So, we need only two quantum gates. The first one is Hadamard gate and the second one is C0 gate. That's all. So, this is one of the reasons bell states are taught first in almost every quantum computing course. So, with just two simple gates, we can create one of the most important gate states. First, the Hadamard gates create the superposition, and then the C0 gates create links the second qubit with the first one. Together, they create the entanglement. So later in the lab, you will see this happen step by step. Now look at this statement. So the two qubit cannot be described independently. This is actually the heart of today's session. Normally, if I ask you, what is the first qubit doing, and you should be able to answer what is the second qubit doing, right? Again, you should be able to answer, but in a bell state, you cannot completely describe one qubit without considering the other. So they become connected. The complete information exists only when we consider both the qubits together. Okay, this is why bell states are so different from the ordinary quantum states. And finally, why are these called as Bell states? They are named after the physicist called as John Stewart Bell. Bell was interested in one of important question: can quantum mechanics produce correlation that classical physics cannot explain? So to answer this, he proposed something called as Bell's theorem. So his work became one of the foundation of modern quantum information science today. So when we say Bell state, we are remembering the scientists who helped us understand the unique nature of quantum entanglement. So now that we know what a Bell state is, let's discuss why entanglement receives so much attention. Like, why is everyone talking about it, and why is it considered one of the greatest discoveries in the quantum physics? So the first point says entangled qubit shows correlation stronger than anything possible classically. Let's understand this carefully. In classical systems, two objects can certainly be related, right? So, for example, two synchronized clocks or two copies of the same document, they are correlated, but their relationship is limited by the classical physics. So quantum entanglements creates much more stronger relationship. So the measurement results remain connected in a way that cannot be explained using a ordinary classical ideas. This is why entanglement attracted so much interest. And the slide says measuring one entangled qubit instantly determines the outcome of the other. So this sentence often surprises people, right? Many people misunderstand it. Let me explain. Suppose we create a Bell state, then we separate two qubits. If we measure one qubit and get 0, and the other measurement will also follow the correlation expected for the Bell state. Similarly, if the first gives 1, the second also gives the correlated result. So the important thing is that the relationship already exists because of the entangled quantum state. Okay, so now let me clarify something. Many people think, like, if the result appears instantly, does it mean information travels faster than light? The answer is no. Nothing is traveling faster than light. No useful information is being sent from one qubit to another during this measurement. The measurement outcomes are correlated, but this cannot be used as a communication system. Okay, this is a very common misunderstanding, so always remember this point. And now let's see where entanglement is actually used. It plays major role in actually quantum communication, cryptography, teleportation, and quantum algorithms. Right? In tomorrow's session, we will actually study about quantum teleportation. You will see the Bell states become the foundation of that protocol. So today's topic is preparing for the tomorrow's concept. Yeah, so today's takeaway is this. Bell circuits are special 2 qubit states, and Bell states create entanglement. Entanglement creates the strong quantum correlation. Those correlations become the foundation for many advanced quantum technologies. And in just a few minutes, we are going to create one ourselves using the two quantum gates. Okay, so now that everyone understands the theory, it's time to move from concepts to implementation. Okay, you can open your qBraid platform. Okay, here what we are going to do in this lab is the objective is to build a circuit that prepares the bell state on the qBraid, and we will create 2 qubit in the known state, and later we will apply the HADMAT gate, and next we will create the CNOT gate and link the qubit 0 and the qubit 1, and later we will inspect whether we have created the bell state using the state vector just like we did in yesterday's session. We will be cross varying that in this lab. After this, we will learn about the measurement part, and later we will execute the measurement on the real quantum computers in the next session. Okay, so our expected outcome should be we should have the equal or nearby amplitudes for both the states. Okay, so you guys can open your qBraid platform. Fine. So, like, all the account creation would have been already done, right? I'll just close and open it again. Yeah, so I'll just log in and launch my instance. So you can wait until your instance is getting launched. you can go back to our folder. Here you can create the new folder, okay, and name it as day 3. Okay, and if you have already downloaded the libraries, like yesterday, if you have already created the environment, you don't need to create it again. If not, you can create the environment just like how we used to do in the day 1 and day 2 session. So if anyone needs to create the environment, can raise your hand so that I can wait until you guys are going to create the environment. Everyone have the environment created, or do you guys want me to repeat the steps again? Okay, ma'am. Anyone else? Okay, then cool. We'll move to the answer. Can we use? Yes, you can use the already created environment because we are not going to install any new package now. Okay, for the state vector implementation, and for next thing, okay, I will help you like import the packages on the existing environment itself. Okay, no need to worry about it. For now, we will be using the same package system. You can use the same one. I'll guide you through that. Okay, then we'll move to the hands-on part. Okay, so you can go inside the day 3 folder and you can create a new notebook and you can name it as bell state vector. Okay, so once you have done that, let me know. I hope everyone is following on the same steps. And later here you need to change the kernel to our already created kernel. Okay, and click on select option and restart the kernel. This is a ritual you need to follow whenever you are using the qBraid platform. Okay, so once that part is completed, we'll move on to our hands-on session. Okay, so now we are inside the qBraid, right? And whenever we write a Python program, the first thing we usually do is import the libraries that we will be needing, right? Think of these libraries as ready-made tools. Instead of writing everything from scratch, we simply import the functions we need. Just a minute. Yeah, so instead of writing everything from scratch, we will simply import the functions we need, and we will go through each import now one by one. Okay, so firstly we will import Qiskit from the quantum circuit, from quantum circuit from Qiskit. Okay, once this one is done, next, so this first library we are importing is the quantum circuit. This class allows us to create the quantum circuits. Without this, we cannot create any qubits or adding gates or building the quantum program. So every quantum circuit starts here. Next, we will from cascade AER, we will import AER. Okay, so we are importing AER, which provides a simulator right now. We are not implementing it inside the quantum computer. Okay, so instead we will use a simulator first to study about the state vector, whether we have created the Bell state correctly or not. In the next section, we will run it on the different simulator like AWS state vector simulator as well as the quantum computer in the second half. Okay, and next we'll import the state vector from cascade dot quantum info. So this one is the most important libraries for our today's lab. And remember, I mentioned that before measurement, the qubit is in the quantum state. We cannot directly see that state by measuring. So the state vector class lets us inspect the quantum state before measurement. So today we will use it to verify our well state has actually been created or not. Next, I'll import the plot histogram from the cascade visualization. Okay, so once you have done this, you can just so after running the circuit, we will obtain the measurement result. So instead of looking at the table of numbers, it's much easier to see them in a graph, right? So these libraries will draw the histogram showing how frequently each output appears. Next, we will import matplotlib library as a plot, like PLT as the alias name. Instead of using the lengthy keyword, we will make it short. Okay, so this is general Python plotting library. We will use it whenever we need to display the graph. Next, we are going to create our backend. Sorry, this is PLT. It's just a variable. Next, we'll create the backend. So here what we will do is we will tell Qiskit which backend to use, and a backend simply means like where the circuit will run. Okay, so today our backend is AER simulator. So every circuit we execute today will run on the simulator. Now let's actually build the Bell state. Okay, so anyone have any questions till now before we build the Bell state circuit? I'm moving slowly because most of them have not been able to like complete the labs in the previous sessions. Okay, so let me go slowly only and we'll make sure everyone is completing their labs. Okay then. So now let's actually build the Bell state. Notice that we are first checking the state vector. We are intentionally not measuring it. Why? Because once we measure, the superposition will get disappeared. So first we will inspect the quantum state only after understanding it, and we will perform the measurement. So you can click on shift enter so that you can shift to the next cell, or you can click on add. You can type QC underscore SV. So cute. So I'm creating a new quantum circuit containing 2 qubits. Right now both qubits are automatically initialized to 0. Nothing has happened yet. Okay, next we'll apply the Hadamard gate. So now I apply the Hadamard gate to the qubit 0. This is the most important step. So before this line, qubit 0 was definitely 0. After this line, it enters to the superposition. It is no longer definitely 0 or definitely 1. Instead, both possibility exist together. So if I skip this step, sorry, the Bell state would never be created. Okay, and now now comes the C naught gate. Okay, so notice the parameters, like 0 means the controlled qubit, 1 means the target qubit. Since the control qubit is already in the superposition, the C naught gate acts on both the possibilities simultaneously. This is the moment where entanglement is getting created. Now let's carefully read the output by okay. So here you will be noticing the 4 amplitudes if you run it. Okay, so each amplitude corresponds to one basic state. The order will be like 0 0 0 1 1 0 and 1 1. Okay, so we'll run these circuits one by one. Make sure to run your import cell before running your this one. Okay, sorry. Instruction. Yeah. So the amplitude for 0, 0 and 1 1 is approximately 0.7071. So the amplitude for 0 1 and 1 0 are 0. Why 0.7071 means if you do the square root of this one, this matches exactly the Bell state equation we discussed earlier. So before measurement, our circuit has successfully prepared the state. Okay, and that means our Bell state has been created successfully. And now we have confirmed that the Bell state mathematically using the state vector. The next step is to measure the qubit and check whether the experimental results also match what we expect. We will add measurements and execute the circuit multiple times and verify that only 0 0 and 1 1 appears with approximately equal probability after everyone completes the hands-on exercise. And we have discussed your observations, and we will take 30 minutes break before returning for the next session on the entanglement verification through the measurement. So these two yeah, you can take for 30 minutes and you can come back by 3:30 so that we can resume our session from there, where we will do the measurement part and we will try to implement the same bell state on the real quantum computers. Okay.
No, ma'am. It is setting the environment. Here the network connection is intermittent, so couldn't able to come up from this. Here the internet connectivity is intermittent, so couldn't able to come up with you. I am setting up the environment. Okay, ma'am. If any doubts, I'll ask you in the next session. Thank you so much. Yes, ma'am. Yes, sir. Ma'am, please you mute itself, ma'am, because my network is hanging. Please, please. Thank you so much. No option, ma'am. Okay, ma'am. I quit and rejoin again, ma'am. No, it is. I hope it will be very noisy. I'll quit and rejoin. No problem. Thank you, ma'am.
Actually, while running the code, I got a error that quantum cycle has no attribute measure all.
Good evening, ma'am. Ma'am, this is Dr. Monica Malik from JSS University, Noida. Uh, yeah, ma'am, sessions are very interesting. That is no doubt. But the only thing is that since although I am from the wireless sensor networks domain, but since this is one of the buzzword these days, yeah, the topics are a little difficult. Like we are finding it difficult, but otherwise your sessions are going very good and we are understanding it well, ma'am. Thank you so much, ma'am. Yeah. Yes, yes, I have never seen any of this. In fact, I'm also coordinating one Atal FDP, that is an offline FDP at JSS University, ma'am, recently. Yeah. Yeah. Thank you, ma'am. Thank you. Yes, ma'am. Yes. But ma'am, still quantum communication and quantum technology is little bit difficult, ma'am. Mm. Yeah. Yeah, yeah. Yeah. And the thing is, whatever we are studying or what we study, there's nothing that we can authenticate it. It seems that it is going in some direction. That is the problem with this. I mean, I'm finding it, ma'am. But otherwise, like attending your sessions, I've attended your session many times, ma'am. But it is always a good experience. I'm learning. I'm learning, ma'am. Thank you so much. Sure. Yeah. Thank you so much, ma'am. Thank you. Okay.
session, we built the teleportation circuit up to Alice measurement, and now we will complete the protocol by understanding how Bob recovers the original quantum state. And the key idea is that Alice measurement alone is not enough. Okay, Bob still has to perform the circuit quantum operations based on the two classical bits Alice sends him. So let's see how that works. Okay, so after Alice measures her two qubits, Bob's qubit is not automatically is in the correct state, right? So instead, its state depends on the Alice measurement outcome. So Alice obtains two classical bits, right? We named it as C1 and C2. Yeah. So Alice obtains two classical bits, and these two bits tell the Bob exactly which correction gate should be applied when it was shared through the communication channel. So that is Q2. Okay. So there are four possible measurement outcomes. So if Alice measures 0, 0, okay. So Bob does nothing, right? That is what we heard it. And if she measures 0, 1, so Bob will apply the X gate to make it happen. Okay, to make it come to this state. And next, if she measures the 1, 0 state, Bob will apply in the Z gate. Okay, so and if like Alice measures the 1, 1. Okay, that time Bob should apply both the X and Z gate. Okay. X and Z gate. Okay, so these corrections gates, what it will do, it will remove the changes introduced during the Alice measurement, and it will also recover the original state of the quantum. Okay, like qubit. So an important observation is that, like, without receiving these two classical bits, Bob has no idea which correction to perform. So his qubit simply appears random, and this is why classical communication is an essential part of the quantum teleportation. And entangle alone it is not at all sufficient. So now we reach the final stage of our teleportation protocol. So once Bob receives the Alice two classical bits, he performs the appropriate correction gate. And after applying that correct operation, something like remarkable happens here. So Bob's qubit 2 becomes exactly the same quantum state that qubit 0 originally had. So here we need to notice something very important, that the original qubit does not still contain the state. So Alice measured it earlier, so it has already collapsed. So the quantum information now exists only on the Bob's qubit. This means the quantum state has been transferred, not copied. So this is why quantum teleportation obeys that no cloning theorem. So the complete protocol combines three ingredients mainly. First, shared entanglement. Next, Alice measurement and classical communication. Next, Bob's correction operation. So together, these allow the faithful transfer of quantum information from one location to another without physically sending the qubit itself. So now that we have understand the complete theory, let's verify it by implementing some remaining part of our protocol in the qBraid. Okay, so so far we have built the teleportation circuit and understood the theory behind it. In this lab, our goal is to verify that the teleportation protocol actually works, and we will complete the circuit and compare the final state of the Bob's qubit with the original state that Alice wanted to design. And we will begin from the circuit we created in the previous lab, and then we will apply the correction operations and verify the results using both state vector analysis and measurement outcomes. To ensure that protocol is reliable, we will test multiple input states instead of just one. And if Bob's final state always matches the Alice's original state, we can confidently say that quantum teleportation has been successful. So let's start this by building the complete teleportation protocol. teleportation circuit. Okay, if someone, for someone, it might ask to restart it. Why? Because we are back after long time. For me only, it is asking. I'll just restart it. No issues. Okay, so the first cell of code I'll just copy paste with you guys so that we will have another half an hour for executing it on the hardware because typing the full code will take some time. So I'll just paste it on the cells. You can just copy paste it. But I'll be explaining you guys about what we have read. Okay. Let me restart. Yes. So here, what we are going to do is, yeah. So we are defining a reusable function that build the complete teleportation circuit. Okay. And first we prepare input state on the qubit 0. Fine. And next we will create a bell pair between the qubit 1 and qubit 2 using the Hadamard gate followed by the CNOT gate. Fine. And then Alice performs the bell measurement. Fine. By applying a CNOT and Hadamard gate. So finally, Bob's correction gates are included in this circuit. Fine. So you can see it here. And to make the circuit easier to understand, we have added the barriers to separate each stage of the protocol. So when we print the circuit, we can clearly see the sequence here. So state preparation, bell pair creation, Alice operation, and Bob's correction stage. So this represents the complete teleportation circuit. Okay. So in the next cell, what we are going to do is this one also I'll just copy paste. I'll be sharing this IPYND file in the deliverables of the today. My team will share it with you guys. Okay. So I think like there are some issues with the audio. I will like address it at the end of the session. I'll answer you guys with that. Fine. Yeah. So here what we are going to do is now we will define several different quantum states to test the teleportation protocol. So instead of testing only one state, we will verify with the teleportation works for multiple input states like 0, 1, plus and minus. Fine. All the things. So for each state, we also define the expected state vector. Fine. And this expected state vector will later be compared with the Bob's constructions. Fine. Reconstructed state using the quantum state fidelity. And this allows us to quantitatively verify whether the teleportation was successful or not. Fine. So next what we are going to do is we will perform our first verifications using the state vector. Okay. So I think one thing we can do, I'll just explain the cells and I'll upload this folder inside the drive and I'll share the drive link with you guys. You can just download and upload it like we did in the first session. Because for doing the task, you need to have this file at any cost. Okay. So at the end of this explanation, I'll share it with you guys. Okay. So here what we are going to do is now we perform our first verifications using the state vectors. Okay. So for each input states, we build a teleportation circuit and we will simulate it. Fine. And finally, we will calculate the fidelity between the Bob's final state and the expected state. So as you can see, every fidelity value is exactly 1.0, right? So the fidelity is 1 means the two quantum states are identical. So this confirms that teleportation perfectly reconstructs the original quantum state for all four test states. Okay. Next, let's see the measurement basis. So here what is happening is state vector verification is useful in simulation, but in real quantum hardware, we only have access to the measurements. So now we will verify teleportation using the repeated measurements. Okay, so we will execute this circuit for 10,000 shots. Okay, and observe the Bob's measurement statistics. Notice that expected behavior will be when teleporting 0, Bob always measures 0, and when teleporting 1, Bob should also measure 1. When teleporting plus or minus, Bob measures 0 and 1 with nearly equal probability. And this is exactly what quantum mechanics predicts. So the small differences are simply due to the statistical fluctuations. So even though measurement outcomes and the teleportation protocol behaves exactly as the expected, right? So until now we have tested on the only on the standard basis and superposition states. So let's make the experiments more interesting by teleporting an arbitrary quantum state. So here how we prepare the state using the pi by 4. Okay. So here again we verify the results in the two ways. First we will compute the state fidelity and it remains essential one showing Bob's recover the correct quantum states, and then we compare the measured probability with the theoretical probabilities. Okay, and the experimental values it will closely match the expected values. Okay. So here you can see it will confirm you that successfully teleportations even for an arbitrary quantum states. Fine. So yeah. So finally here are the complete circuit diagrams for every state test say. You can notice that almost the entire teleportation protocol circuit is identical. The only difference is the state preparation step on the qubit 0. Okay. So everything else, the bell pair creation, Alice operation, and Bob's creation stage remains exactly the same. Okay. So this demonstrates one of the powerful features of our quantum teleportation, and the protocol itself is universal. So it works regardless of the quantum states being teleported, and only the input state changes. The teleportation algorithm remains unchanged. Okay. So before we conclude today's session, I would like to give everyone an hands-on exercise. Okay. So here I think we have legacy first one which is available offline. If it is available online, we can check it first. Okay, it is available online, but I want you guys to work on the different one today, that is IQM Garnet. Okay. The thing is you can use the same syntax to select the hardwares just like yesterday. Okay. Instead of using legacy first ID, you need to define IQM Garnet IDs. Okay. And yeah, so we have successfully implemented and verified the quantum teleportation on the simulator. Now it's your turn to run or execute it on the real quantum computer. So for this exercise, I want you each of you to modify your notebook and run the teleportation circuit on the IQM Garnet. Okay, you can just add a new cell and you can just work on this uh, protocol. Okay, at the end of the cell, you can just add and you can work on it. I'll share the drive link for this. Fine. Yeah. So what is your main task is you need to replace the simulator backend with the IQM garnet, and you need to submit your teleportation circuit as a real hardware job, and you need to wait for the job to be complete and observe the measurement results. Next, we will compare the results with the simulator output and note any differences. Okay, remember, unlike a simulator, real hardware is affected by noise and gate imperfections. So you may not get perfect ideal results. So this is a great opportunity to experience the difference between simulation and the actual hardware execution. So I'll give you like 45 minutes of time. Okay, so we can get back by 4:30 and to complete this exercise. If you face any issues with the backend selections or job submissions, we'll try to figure it out. You can try to do the troubleshooting, okay, or else we'll share the exercise solutions by the end of the session. No need to worry about it. Just give it try for that. Okay, so I hope everyone will execute it. Like I will be not giving you hope that I'll be sharing the answer for this exercise. Try your level best to make sure you are doing this exercise so that you will be having a great understanding about how to use the device in using this qBraid and what are the different results you can observe inside the simulator as well as real quantum computers. Okay. So once that 45 minutes are over, we'll come back together and discuss your observations and the results you obtained from the real quantum computers. Okay, good luck.
Hello, ma'am.
Yes, sir.
Yeah, actually, I want you to let me know this part. So you mentioned replace to replace the simulator backend, right? After that, I could not I could not track.
Yes, sir. Okay,
Can you
okay.
repeat?
So first, you need to replace the simulator with the backend with IQM Garnet. Okay, you need to change the device IDs. Yesterday we worked on related C plus one, right? Same procedure will go for device selection. You need to replace only the device IDs, but defining the variables will be little bit challenging for you. Just give it a try, okay? And you can submit your teleportation circuit which you have built in the simulator. You can submit same variable inside the real hardware, and you can wait for the job to complete. It will take some time to execute on the real quantum computer because of the queues. Okay, and you can observe the measurement results, like what is the difference of using the simulator as well as the real quantum computers.
Okay, ma'am. Thank you.
Yes, sir. So we will get back by 4:30. Will that be okay for everyone? I'll be sharing you the drive link. So give it a try for it and go with that. Before we begin with the today's topic, we will first complete the task that I gave you yesterday. So yesterday's challenge was to run the quantum teleportation circuit on the real quantum computer, right? So specifically the IQM Garnet backend available through the qBraid. So today I will demonstrate the complete workflow from connecting to the hardware and submitting the circuit and retrieving the results and finally interpreting what those results mean. Okay. Okay, like yesterday, if anyone have followed my steps till how to execute the circuit on the AER simulator, you can just resume with what I will be doing today. Okay. And you can launch the instance once you have logged in. Like, is anyone executing the lab like with me, or like anyone like waiting up for the end of the session to me share the code? Just let me know so that I'll be not typing the code, so I can just explain the code, so it will not utilize much time, and we can proceed with our next algorithm implementation. Just raise your hand if you are executing the program along with me. Like yesterday, if you have already executed it, just raise your hand.
Ma'am, yesterday in the second part, I was not able to continue because I had to leave for my classes.
Okay.
So
Okay, sir. No
I think it
issues.
was before 4 o'clock or something, I had to leave. So during that time, I think you had asked to do that teleportation circuit.
Yes,
So
hardware. Yeah. So that one only. So
yeah,
we'll do one thing. I'll just explain the code because we have no much time. Like you guys can just implement it if I share the code, but I want you guys to understand it. So I'll just explain how it can be implemented on the hardware, and later we'll move to the Diet algorithm. Okay, so right, for yeah, like using any qBraid simulator or the quantum computers, what we need to do is first we need to like import the qBraid provider, right? So till yesterday we did till here, till like Bob's correction gates was applied and we verified whether the data was received properly or not, whether the teleportation is successful or not, right? So first step here, we will import the qBraid provider. So this provider will give us the access to all the quantum devices available through the qBraid. Okay, and next we will create a provider object and connect it to the IQM Garnet backend using the device ID. So after that, we print the device information and metadata. Okay, so the metadata will tell us about the details such as whether the device is a simulator or the actual hardware and the number of qubits available inside this. Okay, and how much like credit cost it will take, and supported gates, connectivity, and other hardware specifications. So before running any circuit, it's always a good practice to inspect the backend in which you are going to run your circuits. Okay, next, now we will build the teleportation circuit. Okay, so in this example we are teleporting an arbitrary quantum state which will be prepared using the ry pi by 4 or rotation. So after construction, the teleportation protocol we will be measuring all. Okay, so remember that real quantum computers cannot return the complete quantum state, so they only return measurement outcomes. Okay, so measurement gates are mandatory before submitting the circuit. So finally we draw the circuit just to verify what everything has been built correctly or not. And you can clearly see the state preparation, bell pair creation, and Alice operation and Bob's correction gates, and the final measurements, right? So next, what we are going to do now, we are ready to execute this circuit on the real quantum computer, right? So here we have chosen the 50 shots. Okay, and a shot will be like meaning repeating the same quantum circuit multiple times, right? So you can go for how many ever number of shots you want to just verify your data is correct or not. Okay, the more shots you're going to do, the more validity you will be getting. Okay, the proof of concept you will get whether it is correct or correctly executed or not. Since quantum measurements are probabilistic, we repeat the circuit several times to obtain the meaningful statistics. So we submit the circuits using the run method. Okay, so yeah, immediately after submission, your qBraid will return you the job ID. Fine, think of it this as a tracking number. You can use it to monitor the execution status and retrieve the results once the quantum hardware finishes. So for example, like for this running the job, you might get the output within a minute or 5 minutes. Okay, but there are some circuits whenever you are working on some iterations, it might take days, or because of it might be because of your program, or it can be because of the number of queues available inside these devices. So here you can see in each device there will be queues created. Queues means there are some people which are already like using the same device along with you. So whenever you are running the job, it will be also placed inside some queue. Okay, so mostly the jammed one is always IBM. Why? Because currently this QGSS program is going on, right? So due to that, these jobs are getting queued like a lengthy one. So you can just go for a different device which is available through the qBraid. So yeah, at that time, if you want to track the job IDs, okay, so you can go to their specific cloud account. If you have the what will say job id and job like account to that specific cloud, you can just monitor your job id there also, or you can monitor the jobs here. You will get three state running process. Okay, one will be queued if it is in standing in the queue, and if it is getting implemented inside the hardware, that time it will be showing you the status of running. Okay, and if it is done, it will be showing you the completed state. Okay, so we can use this one. So as I said, this job id, you can use it to monitor the execution status and retrieve the result once the quantum hardware finishes our job. Okay, next, once the execution is completed, we call the job.result. This retrieves the measurement results from the quantum hardware. Okay, and here we are going to print the measurement counts. So there are simply the number of times each 3-bit measurements outcomes occurred across all shots. Okay, so since we executed the circuit 50 times, all of these counts together should add up to 50. Okay, and next step is about analyzing the Bob's qubit, right? So our goal is not to analyze all the 3 measured qubits. We are only interested in the Bob's qubit because that's the qubit that should contain the teleported quantum state. So we extract only Bob's measurement results from the complete bit string. Then we count how many times Bob measured. Okay, 0, 1. Finally, we will convert those counts into the probability. Okay, so now let's understand what these results tell us. So here you can say the hardware returned is Bob measured 0 for 0 point means 29 times and 1 for 21 times. So since the experiment was executed 50 times, so the probability will become like let me draw you some. Yeah. So here you can see. So Bob counted 0 for 29 times, right? And 1 for 21 times. So probability of 0 will be, because we measured for how many times? 50. So probability of 0 will be 29 divided by 50. So how many times we will be getting it? It will be, the total probability will be 0.58. Okay, and similarly for the Bob of counted for 1, that time it will be like 21 divided by 50. So at that time the probability will be 0.42. Okay, so now remember the state we prepared at the beginning, right? Let me just erase this. Yeah. So now remember the state we prepared at the beginning. It was like r by pi by 4 of 0, right? For 0. So how we will represent it mathematically is, okay, is equals to r by pi by 4 of for 0. So for this state, the theoretical probability or approximately like for 0 it will be 0.854 something, and for P1 it will be like almost 0.146. Okay, so on an ideal simulator we would expect values very close to this. Okay, so however we are running it on the quantum computer, so it's perfectly normal for the measured probabilities to differ. So real hardwares, right, it is affected by gate errors, decoherence and readout errors and noise in the physical bits. So these imperfections introduce deviations from the ideal theoretical values. So what's important is not obtaining exactly the same probabilities, but successfully completing the entire teleportation on the real quantum hardware. So this demonstration that we were able to like prepare the quantum state, create entanglement, execution of telecommunication protocol, run it on the real quantum processor, and retrieve the analyzed experiment result. Okay, so this is the exactly how quantum experiments are like performed in the real research as well as in the industry side. Okay, so without any delay, I will be sharing you guys this file, entire file, like along this yesterday's as well as today's deliverables will be shared together. Okay, I will be sharing it with you guys. Okay. So now I officially welcome you guys to the day 5 of our FTP on the quantum computing using qBraid. So yesterday we explored the complete quantum teleportation protocol, and at the end of the session I gave you a small challenge, that is executing the teleportation circuit on the real quantum computer, that is IQM Garnet. Okay, I hope like many of you tried. It's okay if not. I have explained you guys about the concept. I will share the notebook file with you. Guys can try it out from your end. Okay. So today's session is divided into 4 parts. Okay, so first we will execute the complete Jose algorithm and understand how to interpret its result. And next we will perform our lab 15. Okay, we will be by implementing the algorithms ourselves. After that, we will compare how this problem is solved classically versus quantum mechanically. And finally, we will move to the lab 16 where we will test the algorithm using multiple oracle functions. So before starting the today's topic, let's quickly recap what we learned yesterday. We studied the quantum teleportation protocol and saw that it combines quantum entanglement as well as the classical communication. We learned how Alice performs measurement and sends classical bits, and how Bob reconstructs the original quantum state using the correction operation. So today we will build on those concepts the idea of superposition, interference, and multiple multi-qubit circuits. So that we have been learning throughout the week will now come together in our first quantum algorithm. Okay. So let's begin by implementing the complete Jesa algorithm. Fine. We will first build the required oracle circuits, then construct the full algorithm, executed it on the simulator, and finally interpret the measurement results. Okay, and we will by the end of this session you will understand how a quantum computer can distinguish between constant and balanced function using a single query. So let's first understand the problem. Suppose someone gives us a black box function, also called as an oracle, right? So we don't know how it's implemented internally, but we can only give inputs and observe the outputs, right? So we are promised that this function belongs to one of only two categories. So either it is a constant, or meaning very every input produces the same in output, or it is balanced, which means exactly half the input produce 0 and half produce 1. So our task is to determine which type of function it is. Classically, in the worst case, we may need to test many different inputs before we can begin certain. Why? Because the Digesa algorithm solves the same problem with just one oracle query by exploiting the quantum superposition characteristic. So the algorithm follows five steps, five simple steps. Okay. So here we will begin with all input qubits initialized to 0 and prepare one additional output qubit. And next, Hadmat gates place every qubit into the superposition, allowing the quantum computer to represent all the possible inputs simultaneously. We then apply the oracle only once. After that, Hadmat gates are applied again to the input qubits. Finally, we measure the input qubits. Okay, and if the every measured input qubit is 0, we conclude that oracle is constant. If any measured qubit is 1, the oracle is balanced. So now that we understand the theory, let's implement the Jose algorithm ourselves. Okay, we will first create a different oracle function, and then we will build the complete algorithm, execute its using the simulator, and observe how the measurement result tell us whether the oracle is constant or balanced. Okay, you can go to our as usual folder structure which we created from day one. You can create a folder. You can call it as day 5. Okay, so inside day 5 you can create a new notebook and you can rename it. Okay, yes, so as usual, ritual for us to select the kernel which we created. Fine, and you need to restart it. Yeah, so our kernel is ready to be implemented. Now we can proceed with the importing. So first let's import the required libraries. So we will import numpy as, and we'll give it as one alias name. Next, for visualizing we'll use next from Qiskit we will import quantum circuit, which is the important. Okay. Next, we'll import the simulator. Next, let's prepare the backend. And to check whether our backend is ready, we can print. And you can run this. Sorry. Yeah. I hope everyone is following my steps. Okay, so here we will be using the Qiskit to build the quantum circuits and AER simulator to execute them locally. And then we initialize the simulator backend. So if we see like backend ready AER simulator, it confirms everything is configured correctly. Okay, so next we'll define the Oracle circuit. Fine. So remember our oracle will be like representing the unknown function. Fine. So we'll create the circuits. Next will be the circuit inside this function. Next we'll identify like f of x is equals to 0, which means like C not applied. Okay, so we'll return the quantum circuit. Similarly, we'll define our next circuit by using the flipping. I'll zoom it a little bit so it will be visible. Just copy paste it. We'll call it as one. Next, we'll flip the gate. Okay, so for that we will be using the X gate. After defining the functions, I'll explain you like line by line, no need to worry. Okay, just follow my steps. Next, we'll define the balanced inner product oracle. We are going to define the parity. Next, let's define the range. Just put it indentation and define the range also. Yeah. Next, bit oracle balanced one. Okay, let me check the gates. Okay, this is in it. Here too, it is a C node gate. Yes, this is X gate. Let me try to run it. Yes, so it has run successfully. So let me explain each line one by one. Okay, so here first we have defined the constant zero oracle, right? So here we are creating a Python function named as constant zero oracle. Fine. So n qubits, it represent the number of input qubits. Okay, the oracle will automatically create one additional ancilla qubit. Okay, next we have defined the oracle for f of x, right? So 0 for all x, so which means like this is the function documentation. Okay, it will does nothing, and this one is about defining the function. So it will create a quantum circuit. It will contain n qubits, which will input the qubits, and one is the ancilla qubit. So we will label this circuit as the f is equals to 0, so it is easily identified later when we are printing the circuits. And next, this return QC will be returning your Oracle circuit, so it can be inserted into the Dude-Joseph algorithm. Fine. Next is we have created another Oracle function that this time the function always returns 1. Okay. And here we are going to flip the ancilla bit unconditionally. So here we have defined QC is equals to quantum circuit of n qubit plus 1 and name is equals to f is equals to 1. So here what happening is we are going to create another Oracle circuit, and again it contains all the input qubits plus 1 ancilla qubit. Okay, and next we are going to apply the X gate, okay, that is the NOT gate on the ancilla qubit, and n qubits refers to the last qubit, which is the ancilla qubit, and this changes its states from 0 to 1. Okay, and next we have return QZ, which means like it will return the complete constant 1 oracle. Fine. Next, what we are going to do, we will create one balanced oracle. So the output will be depending on the parity bit, so that is XOR gate. So for all the input qubits we will be applying the parity gate. So here what happens is the function will check whether the number is 1 or which is even or odd, and this is called the parity function. Fine. So here we are going to balanced because exactly half of the inputs will be 1 and half of the inputs will be 0. So here we need to apply the parity function. So here we have defined QC is equals to quantum circuit and qubit plus 1, and name we are going to give it as parity. So we are going to create this balanced oracle circuit and we are going to label it as parity circuit. Okay, and next we are going to define some range. So here what we are doing is we are calling the for loop, right? A loop through every input qubit. If there are 3 input qubits, so these loops run for qubit 0, qubit 1, qubit 2. And next we have applied the C NOT gate. So apply a controlled NOT gate, and controlled bit 1 will be the current input qubit. Next target 1 will be the ancilla qubit. Okay, and next what the final ancilla state becomes the XOR, that is the parity of all the inputs. Next we are going to print the circuit. Fine. Next we are defining a another circuit called as balanced first bit oracle. So it takes the number of inputs qubits as input. Okay, and this oracle is a balanced function. So here what happens is we will create a quantum circuit with n qubits. Fine. And 1 ancilla qubit. So we are going to name this circuit as f is equals to x0. And next we are going to apply the C NOT gate. Fine. And control bit is the qubit 0, and target bit will be our ancilla qubit. Next, this means the if the first input qubit is 1, means the ancilla bit will get flipped. If the first input qubit is 0, it will not do anything. Next we are going to print that circuit. Fine. And we will return the complete oracle circuit. So next, another circuit we have defined here is negated parity oracle circuit. So this one computes the opposite of NOT of the parity function. Fine. So here what happens is it will take the opposite of the balanced function and still give you the another balanced function. Like half of the outputs remain 0 and half remain 1. Next we are going to create the oracle circuit. Okay, and it contains all the input qubits plus 1 ancilla qubit, and we are going to name it as not para means negate of parity. Okay, and next again we are going to call the for loop to loop through every input qubit. Fine. Next, each input qubit controls a C NOT gate. Okay, to the ancilla bit. So this computes the parity of all the input gates. Okay, so this gate will make sure it will be like computing or like parity. So here next we are going to apply the X gate, right? That is the NOT gate, which is classical NOT gate, but poly X gate act as a classical NOT gate. That's why I'm mentioning everywhere X gate as the NOT gate, so it will be easy for you to understand. So here we are going to apply the NOT gate on the ancillary qubit. Fine. So this will flip the parity result. So if the parity was 0, it will become 1. If the parity was 1, it will become 0. Next, we are going to return the complete oracle circuit. So now we have defined our 4 different oracle types. So 2 constant oracles always return 0 or always return 1, and 2 balanced one. So here one depends only on the first input qubit, and the other computes the opposite of the parity function. Okay. Okay, so next let's display these circuits whatever we have defined it here. Fine. Let me. So first for oracle, if it is like n is equals to 2, so we'll create circuit for n is equals to 2 and we'll print. Let me type the code first. I'll explain you about each line. Okay. Okay, I forgot to close. Yeah, so here we are going to display example of Oracle circuit using two input qubits. Okay, and next we set the number of input qubits to 2. So therefore Q0 and Q1 are the input qubits. So one extra ancillary qubit, that is Q2, will be added automatically. So total qubits are 3. Okay, and next this line, it is about like printing a heading before displaying the circuits. So it will remind us that Q0 and Q1 are the input qubits and Q2 is the ancillary qubit. Fine. So next we have called the for loop. So we start for loop. This loop will go through each oracle one by one. Okay, next first oracle always returns 0, and next one, second oracle, it will always returns 1. Next we have third oracle that computes the parity function for all the input qubits, so it is a balanced oracle. And next we have the fourth oracle. Fine, that is the like output depends on only on the first qubit, sorry, input bit, and it is also a balanced oracle. Okay, and next we will be closing it, like calls the current. Next what we are going to do is we'll call the current oracle functions using the n is equals to 2. So we will create a corresponding quantum circuit and store the variable oracle. Okay, so for example, it will be like first iteration it will create a constant 0 for oracle, second iteration it will create 1 oracle, and third one parity, and fourth one it will be balanced. Yeah, so that is the first bit oracle. Okay, and next line we are calling the print, right? That is this one. So print, we are going to print the oracle's name before displaying its circuit. Okay, and yeah, so finally we are calling the like drawing the circuits. Fine, and instead of just showing the code, we can just actually see the gates using the inside the oracle. Think there is little bit indentation problem. Let me check it out. Yes, this is the one, right? Yeah, so okay, so here we have built like printed the same way how we have defined inside. Okay, so I think like little bit indentation problem was there, no worries about that. Okay, so here what we are doing is you can check the output. So we asked Qiskit to draw all the 4 oracle circuits for 2 input qubits, right? So here Q0 and Q1 are the input qubits, while Q2 is the ancillary qubit or the output qubit, you can say. So you can notice that each oracle has implemented a different functions. Okay, so for example, we have the Q0, Q1 and Q2. There are no gates in these circuits. So none of the qubits are modified and the ancilla qubit is never flipped. So which means the oracle always returns 0 and regardless of this input. So this is why we call it as a constant function. Fine. Next we have the f is equals to 1 constant, and here you can see the output. Fine. So here what happens is q0 and q1 doesn't have any gates, but there is one x gate on the q2. So the x gate, what it will do, it will be flipping 0 to 1 or 1 to 0, right? So no matter what the input is, the ancilla is always flipped. Okay, so here again every input will give you the same answer, so it is called as constant function. And next we have the parity one. So here you can see C naught gate connecting the input qubits to the ancillar qubit, right? So here what does that mean is Q0 controls the ancillar qubit and Q1 controls the Q1 also controls the ancillar qubit. Okay, so every input qubit contributes to the final output. So this compute will be becoming like f of x is equals to x0 plus x1, which means XOR for the both the qubits. So here here the outputs will be like half of it will be 0 and half of it will be 1. So we are calling it as the balanced oracle. Okay, and next if you scroll further, you will be seeing the only C naught gate, right? So only the first input qubit, that is qubit 0, controls the ancillar qubit, right? So if q0 is equals to 1 means the ancillar will flip, or if q0 is 0 means it will not do anything to the ancillar bit. So here f of x will be x not only, not both the one. So here it is also called as a balanced function, but two outputs will be 0 and two outputs will be 1. So it is called as like balance. But the output of the ancillar bit depends only on the first input qubit. Okay, so yeah. So from these circuit diagrams, we can clearly see the difference between the constant and the balanced oracles, right? And constant oracles either do nothing or always flip the ancillar, while the balanced oracles, it will use the C naught gate, like gates controlled by input qubits. So in the next step, we will plug these oracle circuits into the Dude-Jose algorithm and see how a single quantum execution can identify whether the oracle is constant or balanced. Okay, so we'll meet at 3:30 today. We can have only like 15 minutes of break because we have lots to discuss about the Dude-Jose algorithm. Okay, so we will resume it by 3:30. Fine. Yes. So, welcome back everyone. Before we continue with the next hands-on session, let's take a few minutes to understand why Dude-Jose algorithm is actually important. Okay, so far we have built the circuit and seen how it works. But the real question is, why do we even need this algorithm? Like, let's just compare it with the classical approach. Okay, so yeah. So imagine you have given the black box function, also called as an oracle, right? So, and your task is to determine whether it is a constant or balanced. So in the classical world, there is only one way to do this. Okay, so you keep testing the different inputs one by one until you are completely sure about the answer. So in the worst case, if there are an like n input bits, you may need to check like 2 power n minus 1 plus 1, right? So different inputs before you can confidently decide. So for example, if the input is 4, okay, let me just draw it off. Okay, So what was our, like, if there is an n number of input bits, so what we need to check is 2 power n minus 1 plus 1, right? So if our n is equals to 2, for example, so at that time what happens, 2 power 2 minus 1 is 1 and plus 1. So we will be seeing the, sorry, 3 possible inputs, right? So for example, if it is 4 means 4 minus 1 will be 3. So 2 power 3 plus 1. So 2 power 3 is 8. 8 plus 1, yeah, 8 plus 1, 9. So we will be seeing these many possible inputs. So in the worst case, you might have to test up to 9 different inputs, okay? So but the Dude-Jose algorithm does something remarkable here. So instead of checking multiple inputs individually, it uses quantum superposition to evaluate all the possible inputs simultaneously and needs only one query to the oracle, so regardless of how many input qubits there are. Okay, so as the number of input qubits increases, this difference becomes much larger. So this is one of the easy like earliest demonstration of the quantum advantage. Now, does this mean every real world problem works exactly like Dude Josa? No, not really actually. So, the problem itself is somewhat artificial and was designed mainly to demonstrate the power of our quantum computing. So, however, the ideas behind it are extremely important. We learned how to use superposition and how an oracle can encode a problem and how quantum interference helps us extract useful information. So these same concepts appear again in more advanced algorithms like Grover search and Shor's factoring algorithm. So even though GeoGebra itself isn't solving a practical industrial problem, it builds the foundation for understanding many powerful quantum algorithms. So now it's time for our final hands-on activity. In the previous lab, we built the Dude-Jose circuit and tested it with the oracles, right? One oracle. So in this lab, we will reuse exactly the same circuit and simply replace the oracle with different ones. We will test the constant 0 and constant 1, balanced parity and balanced first bit oracle. So after running the circuits of each case, we will compare the measurement results. Remember the rule we have learned: if the measured output is all zeros, the oracle is constant. If the measured input is anything other than all zeros, it will be balanced. Okay, so by testing multiple oracle types, we will verify that the Dude-Jose algorithm correctly classifies every oracle using just a single quantum query. So with this concepts clear, we'll now switch back to the qBraid and implement our lab together. Fine. Yes. I'll just restart it. Yes. Yeah. So let me create a dude user circuit. So for that I need to store it inside the function. So I'll create one function here called as dude user circuit. Okay, why my variables are not coming? Because I have forgot to restart my kernel. So let me restart it. Okay, so here what I have did is I'm creating a function that builds the complete Gauss circuit. So it takes two inputs, that is the oracle circuit and the number of input qubits. And next we need one extra qubit called as ancilla qubit, right? So let's define the ancilla qubit now. So total bit will be how much it will be. If n is equals to 2 bits, we will be having two input qubits as well as one ancillary qubit. So total qubits in general, how we will define underscore total number of input qubits plus 1, which is an ancillary qubit. Okay, so that the total number of qubits will be input plus 1, that is 3. Okay, if n is equals to 2. So next we are going to create the quantum circuit. Okay, so we'll call a variable to store our quantum circuit. Let me run this import module once again. We'll define the qubits used. So here what I'm doing is it will be creating the quantum circuit. So the circuit will be having total qubits, that is quantum qubits. Okay, and n qubit is the classical bits to store the measurement results. Fine. So you can notice that the ancillary qubit is not, we are not measuring it here. Okay. Next we are going to initialize the ancillary qubit to 1 using the X gate. So we'll apply the gate on the quantum circuit. So initially, like every qubit is 0, right? So the X gate flips the ancillary from 0 to 1. Next, we will call the loop to go through every qubit. Okay. Okay, next what we are going to do is Hadmat gate we are going to apply to the every qubit. Okay, so okay, so when applied, like Hadmat gate is applied to the every qubit, what happens? We will carry qubits becomes the superposition of all the inputs, right? So ancillary becomes the state of how we will be representing the like superposition state. It will be like magnitude of 0 minus 1 divided by square root of 2. Okay, so when you apply the Hadmat gate, it will make that all the qubits to be in the superposition, and next it will allow and the oracle to encode the information as the phase. Okay, Next, what we are going to do is we are going to like create a barrier which will not like affect any computation, but let's define it out. Okay. Yeah. Let's create the barrier. Create the name for this as superposition. Next, we are going to apply the oracle. Okay. Excuse. Okay, so here we are going to insert the oracle into our circuit. So depending on which oracle will be, like we pass, so the circuit will behave as either a constant function or a balanced function. Okay. So again, this barrier is only for visualization. We will create one like label for that, just for visualization. Label. Okay, next what we should do, we need to apply the HUDMAT gate only on the query qubit. Okay, so let's do that. If we want to apply it on specific one, again we need to call the for loop. We'll define the range. Next we'll apply the HUDMAT gate. Next we'll create the barrier just for the visualization. And we'll define it as interference. Okay, so here what happens, why we are calling it as interference, because to define this ADMAT gate will create the quantum interference. So this interference, what it will do is it will combine all the phase information and it will introduce information introduced by our oracle into the measurable result. Okay, so yeah, so again we are just separating the stages visually by writing, like giving the label for that. Next, now finally we'll measure our like only the query qubit. So for that we need to measure it by define the range so that Okay, so this measurement will tell us whether the oracle was constant or balanced. And next we are going, like here we have called the just a circuit. Next, what we'll do, we'll choose like again the input qubit as is equals to 0, and we'll check the possible like outcomes. So we'll define n is equals to 2. Next, we'll select the balanced parity oracle. Next, finally, like the complete use user circuit will be created using that oracle. So for that, we need to call the function, which the function which we created for printing this circuit using the oracle. Okay, and let's print it out. Next, we'll print the circuit. And we'll run this. Yeah. So here you can see the output, right? So we have created our UGSS circuit for a parity function, and we have defined n is equals to 2. You can see all the stages differentiated here, how the superposition was created, and oracle function using, we have created the interference. Okay, now let's run the algorithm. Okay, so like the power of our new user is that like single query, it will suffice to determine whether f is constant or balanced. So if the measure result is 0, it will be constant, or if it is like, if there is any other results than that, it will be like balanced. Okay, so now what we are going to do is we will be experimenting this one using 3 input qubits. Okay, so we are going to give n is equals to 3. Okay, and next what we are going to do is we will create a list containing all the oracle function that we want to test. Okay, we'll store it inside the oracle. We'll call the list of all the oracle functions. That is, first one, f is equals to 0, which is a constant one. Right. The function created for this is constant 0 oracle. Constant. Next, we'll call our another constant function where we will be having the f is equals to 1. And the function we created for this one is constant or one oracle, right? Yes. Okay. Next, we'll call the balanced one, which we created using the parity function. It's called that function. Okay. And we'll call it as balanced. Next, we'll call our another balanced one, which was created using xgate. And the function created for this one is balanced first bit, right? So because it depends on only first bit input, the ancillary bit will get flipped. Next, using the negate of the parity one, that is, this is also a balanced function. And we call this one as balanced negated parity oracle function. Okay, and we'll change this to balanced. Okay, and let's close the list. Okay, so let me explain each function again once. Okay, so first we have oracle, always output will be 0, so we will be having the expected answer as constant. Next we have oracle, always output will be 1, it is also a constant, right? And third is parity function, so half the input will give you 0 and half the input will give you 1. So one is that. So but it will be still be balanced, right? So since it is like having half of the, it is 0 and half of it is 1. Next we have the output, which depends on the first input bit. So but even though it is depending on first input bit, the output will be still balanced. Next we have the we have called the opposite of the parity, and it is also a balanced function. Okay, next we need to print these statements simply to display the neat result table. Okay, clean, let's print it. Print. So why we are printing like this is just to like simply display a neat result table. Okay, and next now we test each oracle one by one by calling the for loop. Okay, next we'll build the dual user circuit using that oracle. Pass the parameters to build that circuit. Next we'll run the circuit once. Okay, so dual user requires only one query. So next we'll extract the measured bit string. Okay, let me restart the server. Okay. since it got restarted. Why? Because if you are keeping it like for more than hour, if you're running your like notebook still, it might automatically get restarted. Okay, no need to worry about it. So next what we are going to do is we are going to define the decision rule here. Okay, so if like output is all zeros, it should be constant, and otherwise it should be balanced. So we are defining that function here. So verdict will be constant if measured zero, or else it should be balanced. So here we will check whether our prediction is matches with the expected oracle type or not. Okay, next what we will do, we will print one row in the results table. Okay, so we will print all the data here now. We'll label it. We'll print all the oracles classified. And then we'll run this cell. Before that, let me run the import cells. Okay. And terminated string. Where? Here, sorry. Oops. Something is missing, right? Okay. I called the wrong function here. Okay. Yeah. Okay, so here let's go through one by one now. So here F0 means it is mentioned like all zeros means constant function. Okay, next we have even though Oracle always inputs 1, the interference still produces all 0. Okay, so no need to get confused here. So it is correctly classified as constant function. And next, since the output is not non-zeros, fine, not all zeros, the algorithm identifies it as the balanced function. Next we have for x0, that is 0, 0, 1. So again it is not all zeros, so it is called as again balanced function. And next again we have finally the negate of parity one, which is also not a non-zero functions. It is also called as balanced. So final lines, it is saying that all oracles correctly classified with the single query. Okay, so here you can do one thing, like you can like run it with the different multiple shots by calling it like for the same number of input qubits. Okay, so you can give n is equals to 3 and run the shots for 1000, 10,000, and it's up to you. Okay, and you can check the outputs whether it is classifying correctly as a like constant or balanced at the end. Okay, you can give it a try for this one. Okay, uh we'll wait for 10 more minutes. I guess everyone is following me, or shall I only execute the exercise? Okay, I guess I'll just explain you the code itself. Fine. So try it out yourself at your from your end once. So here we are going to define 10,000 shots. Okay, and what we are going to do here is like we will be giving the like input as 3. Fine. Just a minute. Yeah, so we are going to take the 3 input qubits, and next we will run the circuit for 10,000 times, and this will help us observe the probabilities instead of one single measurement. Okay, and next we are going to list out all the oracles to test. Next we will create 4 graphs. Okay, so we will create like yeah, so one for each oracles. Like we have 4 different functions, we will create 4 graphs for each oracles. Okay, and next we will generate all the every possible 3 qubits. Fine, state inside this. So here you can see the final output as 0, 0, 0, which is classified as a like single signals. We are getting only a single output, which means it is a constant. If we are getting other than the zeros, it is like appearing as what you'll say balanced. Okay, so next we will loop through every oracle. Fine. Next what we are going to do is we will create a circuit again, and we will execute it for 10,000 times, and we will convert the counts into the probabilities. Here all the green it will be saying like 0, 0, 0, and the blue all others are other than 0 output. So we have drawn the bar for that. Okay, and next what we are going to do is we'll observe the output now. So first graph you can see f is equals to 0. So only 0, 0 appears, means probability is equals to 1, which is constant. And second graph you can see f is equals to 1. which means like again only 0 0 0 is there. It is also a like constant. But the parity one, you can see third graph, which is not at all 0 0 0, right? Other than 0 means it is a balance. And fourth graph is also like it is not only a 0, it is all like other than 0 is also occurring. It is also a balanced function. Okay, so here bottom message, if you see, constant is only 0 0 0 and balanced never 0 0 0, which means like this summarize the Judge decision rule. Next, what we are going to do is we will generate a value of n from 1 to 20. Okay, and next we will calculate the worst case of classical queries. And next, quantum always needs exactly one query, right? So for this, we will create the graph. And here we will plot saying that red line will be for classical and blue line is for the quantum. Okay, and next we are going to use a logarithmic scale because classical values becomes very large. Okay, so next we will display the graph using the plot.show, and next we will print a comparison table using by defining all the values here. Okay, and let's see the output here now. Okay, so firstly we have the table where n is equals to 1, which means like classical is equals to 2 and quantum value is equals to 1. So next n is equals to 5 means we will be having the classical as 15 and classical as 17 and quantum as 1. Next, if n is equals to 10 means classical is 513 and quantum is 1. So n is equals to 20, again classical times it will be giving you 5 to like 5 to 4 to 8 9 and quantum is equals to 1. So here in the red line you can see represents the classical algorithms. As the number of input qubits increases, the number of oracle queries grows exponentially. The blue line represents the Judge algorithm. Okay, so it always stays at one query regardless of the number of input qubits. So this clearly demonstrates the quantum speed up achieved by the Judge algorithm. Okay, next we are going to scale it up. Okay, we will print the heading called as scaling test which we are going to do, and next we will test the algorithm for different numbers of input qubits. Okay, and next for every value of n we will test both constant oracle and balanced parity oracle. Yeah, balanced parity oracle. Okay, and next we are going to create the oracle function. Okay, next we will build this circuit. Once we have done that, we will run the circuit and read the measurement results, and we will classify it as an a constant or balanced, and will verify the correctness by defining the verdicts. Okay, and we will print the results. So here you can see like final output, every test passes successfully, right? So here for all the input sizes, whether there is a 1 input qubit or 5 input qubits or even 10, the Judge algorithm still identifies the oracle correctly using only one oracle query. Okay, so this confirms that the algorithm scales correctly and its behavior remains independent of the size of the input. Okay, so yeah, that concludes our hands-on sessions for today. So like I'm not getting any proper response. I don't know like whether to continue with the discussion and quiz, but I'll just try my best. Okay, so we'll have one discussion round where you can share your own thoughts on what you have learned today on the Judge. Okay, so here the question is like Judge solves a fairly artificial problems. So why do you think it is still considered an important results in the quantum computing? So what does it prove about the potential of quantum computers even if the problem itself is not a practical? Okay, that's okay. I will answer this one. So, yeah. So, at first glance, the dual user algorithm may seem artificial because we don't usually encounter problems where we only need to determine whether a function is constant or balanced, right? So, however, the importance of this algorithm is not the problem itself. It's like what the algorithm proves. Okay, and it was the first algorithm to clear demonstrate that a quantum computer can solve a specific problem using fewer oracle queries than any classical algorithm. In the classical case, the number of queries increases exponentially with the number of inputs, but in Ute algorithm always requires just one query. Okay, so most importantly, it introduces the fundamental ideas behind the quantum computing, like superposition, phase kickback, or interference, and oracle based computation. So these same principles are used in more practical quantum algorithms such as Grover search and Shor's factoring algorithm. So in real world applications, similar speedups can be used in areas like database search or optimization problems, cryptographies, as well as machine learning and scientific simulations, where exploring a very large search space efficiently is important, right? So while the problem itself may not be direct practical, the concepts that it teaches are extremely valuable. So that's why Dujosa remains. Sorry. Yeah, sorry for that. I just got disconnected. Yeah. So where were we discussing, right? Yeah. So while the problem itself may not be like directly practical, but the concepts it teaches are really a valuable one. Okay, so that's why Duke Jersey remains like foundation for the algorithms to study in every introductory quantum computing course. Does anyone still wants to like share any thoughts on this? I'll be happy to listen to that, or we can conclude the session. Does anyone want to share points about your user algorithm? Okay, no issues. So before we conclude today's session, let's quickly look back at what we have accomplished till now. Yeah, thank you, ma'am. Okay, so today we have learned the Ducho's algorithm, which can distinguish between constant and the balanced functions using just a single oracle query. And this was our first complete quantum algorithm and a clear example of quantum advantage. So we also saw that this speedup comes from the combination of superposition, interference, and oracle-based computation, not because quantum computers are simply faster, but because they process the information differently. So if we look back over the last few 5 days, we have built our understanding step by step, and started like we started with qubits and quantum gates, and learned about the CNOT gate and entanglement. And we have explored quantum teleportation and today brought all of those concepts together in a complete quantum algorithm. So I encourage all of you to continue experimenting with qBraid and try modifying the circuits and create your own oracle functions and even build a small projects based on the concepts you have learned during the FDP. Yeah, so thank you all for your active participations throughout these 5 days. I hope this program has given you a strong foundation to begin exploring quantum computing further. So with that, we have come to the end of today's session and the FTP. I would like to know, open the floor for any questions or discussions. It can be about today's or any of the hands-on exercise on qBraid or even a topics we covered over past 5 days. Please feel free to ask anything. There are no small questions. I'd be happy to clarify any concepts or discuss how these ideas can be applied in teaching or research. If there are no further questions, I would like to sincerely thank each one of you for your time, participation, and enthusiasm throughout the FTP. I wish you all the very best in your journey into the quantum computing. Thank you and have a wonderful day.